Right now you are looking at a lie. Not a deliberate one, not a conspiracy constructed by anyone with an agenda. A lie built into the architecture of human perception itself, reinforced every time someone looks up at a clear night sky and feels in that quiet and wordless way that they are seeing everything. That the darkness spread above them, salted with light, represents the full account of what exists. That the universe, vast as it obviously is at least in principle the kind of thing that can be looked at. It cannot. What you see when you look up is a local sample, a neighborhood, a single page torn from a book whose total length no measurement we possess can determine, handed to you by physics, and labeled without irony, the observable universe. The word observable doing enormous work in that phrase, doing the work of concealing how much the second word universe has been quietly redefined to mean something far smaller than it sounds. There are approximately 2 trillion galaxies within the sphere we call observable. 2 trillion. Each one, a gravitational city containing hundreds of billions of stars, each star a nuclear furnace burning at temperatures that would reduce any matter we have ever touched to plasma in a fraction of a second. The numbers involved in describing just the visible portion of the cosmos are so large that the human nervous system has no genuine response to them. You can say 2 trillion. You can hear 2 trillion, but you cannot feel 2 trillion the way you can feel the weight of a stone or the distance to the end of a street. The number passes through comprehension without leaving a mark. And yet that number 2 trillion galaxies, a figure so large it sits beyond the reach of any intuition we possess, is almost certainly a vanishingly small fraction of what actually exists. Not because our telescopes are too small, not because our instruments lack sensitivity, not because the universe is hiding behind something we could in principle move. The fraction we can see is small because the physics that produce this universe, the same physics that produce the carbon in your body and the nuclear reactions in the star, 93 million miles from where you are sitting, guaranteed at the moment of its own operation that most of reality would be permanently, structurally, irrevocably beyond the reach of any observation any being inside this universe could ever make. The wall was not placed there by accident. The wall was placed there by the same process that built us. That is what this journey is about. Not just the size of the universe, which is the easy part of the story, and as it turns out, the least interesting part. This is about why the universe is the size it appears to be, why the boundary sits where it sits, why the physics that solve the deepest problems of cosmology left us as a direct and unavoidable consequence permanently blind to the overwhelming majority of everything that exists. And why the fact that we know this, the fact that we can calculate it, reason about it, and sit with its implications on a quiet night, is perhaps the most extraordinary thing about the situation. If you find yourself drawn to questions that do not resolve cleanly to ideas that leave you slightly altered after spending time with them, then do me a simple favor. Hit that like button and subscribe to this channel. It genuinely helps this work reach the people it is meant for, and it costs you nothing but a moment. Get comfortable. Turn down the lights if you have them. What follows is not a short journey, and it does not end in reassurance, but it ends somewhere true, and that in the end is the only destination worth traveling toward. Let's begin. There is a moment, if you have ever stood outside on a clear night, far from city light, when the sky stops feeling like a backdrop and starts feeling like a depth. The stars are no longer points on a surface. They are objects at different distances receding away from you in every direction, and the darkness between them is not empty but full of things too far or too faint to see. The universe acquires volume. It becomes for a moment three-dimensional in a way that the mind can almost grasp. That feeling is accurate. And it is also profoundly incomplete, because what you are seeing in that moment, every photon arriving at your eye from every direction, represents light that has been traveling toward you for at most 13.8 billion years. That is the age of the universe. That is the maximum time any signal could have been in transit since the cosmos began. And so the sphere defined by that travel time, the sphere of everything from which light has had time to reach us, is what we call the observable universe. It is defined not by the extent of space itself, but by the speed of light multiplied by the age of everything. But here is where the first piece of the puzzle falls into place, and it requires you to hold two things in your mind simultaneously, that at first seem contradictory. The observable universe has a radius of approximately 46.5 billion light-years, not 13.8 billion, 46.5 billion. The light we are receiving from the most distant objects we can detect left those objects 13.8 billion years ago, but those objects are not 13.8 billion light-years away. They are 46.5 billion light-years away, right now at this moment, because the universe has been expanding the entire time that light was traveling toward us. Space itself has been stretching. The universe is not a static container into which galaxies were placed and through which light moves at a fixed speed across a fixed distance. Space is dynamic. It grows. And while a photon was making its 13.8 billion year journey toward your eye, the object that emitted it was being carried further and further away by the expansion of the space between you and it. By the time the photon arrives, its source has moved, not because the source is traveling through space, but because space itself has accumulated between you and it the way new fabric appears between two buttons on a shirt being stretched. The distinction between these two distances, the light travel distance of 13.8 billion light-years and the current co-moving distance of 46.5 billion light-years, is not a technicality. It is the foundation on which everything else in this story rests, because it means that the observable universe is not a sphere 13.8 billion light-years across. It is a sphere 46.5 billion light-years across, and the difference between those two numbers is entirely accounted for by the expansion of space during the journey of the oldest light we can detect. This expansion has a name, it has a history, and its history is the first chapter of the story of why most of the universe is hidden from us forever. Edwin Hubble did not set out to discover that the universe was expanding. In the 1920s, working at the Mount Wilson Observatory in California with its 100-inch Hooker telescope, then the largest in the world, he was trying to resolve a debate about whether the spiral nebulae scattered across the sky were structures within our own galaxy or separate galaxies, comparable to the Milky Way but enormously far away. The debate had been running for years, which gives you a sense of how recently the basic architecture of the cosmos was unknown to us. There were serious astronomers in the early 20th century who believed the Milky Way was essentially synonymous with the universe, that everything visible in the sky was part of one structure, and that the fuzzy spiral shapes photographed through telescopes were simply gas clouds within that structure. Others suspected they were what we now know them to be: entire galaxies, each containing hundreds of billions of stars separated from us by distances that made the distances between stars within our own galaxy look trivial. Hubble settled the debate. Using a class of variable stars called Cepheids, stars that pulsate in brightness with a period directly related to their intrinsic luminosity, he was able to measure the distances to several of these nebulae. The Andromeda Nebula, he determined, was roughly 900,000 light-years away, a figure later revised upward to about 2.5 million light-years. Whatever it was unambiguously outside the Milky Way. The nebulae were galaxies. The universe was vastly larger than anyone had thought. But Hubble also noticed something in the data that was in retrospect even more consequential than the distance measurements themselves. Nearly every galaxy he observed was redshifted. The light from distant galaxies was stretched toward the red end of the spectrum, the signature of an object moving away from the observer. And more than that, the farther a galaxy was, the more redshifted it appeared. The recession velocity was proportional to the distance. Double the distance, double the recession speed. This relationship, now called Hubble's law, was the first observational evidence that the universe was not static. Everything was moving away from everything else. Space was expanding. When Albert Einstein heard this result, he reportedly called his earlier introduction of a cosmological constant into his equations of general relativity, a term he had added specifically to produce a static universe, the greatest blunder of his life. The equations had always been telling him the universe was dynamic. He had not believed them and had modified them to force a static solution. Hubble's data vindicated the original equations. Space was not static. It never had been. But here is what Hubble's observation does not tell you, and what took decades of subsequent work to establish with the precision required to calculate the numbers we are now discussing. The expansion of space is not uniform over cosmic history. The rate at which space expands has changed over time. In the very early universe, it was dominated by radiation, then by matter, and in each of those epochs, the expansion rate evolved differently. And in the last 5 billion years or so, the expansion has been accelerating, driven by something we call dark energy, something we do not understand at a fundamental level, but whose effects on the geometry of space-time are measurable with extraordinary precision. It is that acceleration, that late-time speeding up of the expansion, that creates the most consequential boundary in all of cosmology. Not the boundary defined by the age of the universe and the speed of light, the 46.5 billion light-year particle horizon we discussed a moment ago, but a different boundary, a smaller one, a boundary defined not by the past but by the future, by what the ongoing and accelerating expansion of space will do to the fate of light currently in transit between us and the distant universe. This boundary is called the cosmic event horizon, and it currently sits at approximately 16.6 billion light-years from us. The distinction between the particle horizon at 46.5 billion light-years and the event horizon at 16.6 billion light-years is the distinction between what we can see and what we can ever interact with again. The particle horizon tells us how far back in time and how far out in space we can currently observe. The event horizon tells us something darker and more final. It marks the distance beyond which any signal sent today, any photon emitted at this moment, in any direction, will never reach its destination, not because there is anything wrong with the signal, but because the expansion of space between here and there will outpace the signal's travel faster than it can close the gap. Think of it as running toward a finish line that is itself moving away from you. If it moves faster than you can run, you never close the distance. If space is expanding faster than light can traverse it, light emitted today will never cross the gap to a galaxy beyond the event horizon. And because dark energy appears to be a permanent feature of this universe, a constant energy density of empty space that does not dilute as the universe expands, this situation does not improve with time. It gets worse. The event horizon is not a temporary obstacle waiting for a future technology to overcome. It is a permanent feature of the universe's geometry, built in by dark energy and tightening with every passing year. There is a third boundary worth naming because it appears in the equations and has its own physical meaning. The Hubble sphere sits at approximately 14.4 billion light-years and marks the distance at which galaxies are currently receding from us at exactly the speed of light. Inside the Hubble sphere, the recession velocity of galaxies is less than the speed of light. Outside it, they recede faster than light. This does not violate special relativity, which only forbids objects from moving through space faster than light. It says nothing about the rate at which space itself can expand. Two galaxies separated by a large enough distance can be carried apart by expanding space at any speed whatsoever, including speeds far exceeding 300,000 kilometers per second, and neither one violates any physical law. Doing so, what the Hubble sphere tells you is something more subtle. A photon emitted right now from just outside the Hubble sphere, pointing toward us, is in a region where space is receding from us faster than the photon can travel through it. The photon is moving toward us, but it is losing ground. However, the Hubble sphere is not fixed. As the universe evolves, the Hubble sphere grows in co-moving coordinates, and a photon that is currently losing ground may find itself, after billions of years of travel, in a region where the recession velocity has dropped below the speed of light. At that point, it can finally begin making progress toward us. This is why the particle horizon at 46.5 billion light-years is larger than the Hubble sphere at 14.4 billion light-years. It encompasses all the photons that have been on those long, initially losing journeys and eventually made it to us. 3 spheres. 3 different answers to the question of how large the observable universe is, depending on which question you are actually asking. The particle horizon for what we can currently see, the event horizon for what we can ever again receive information from, the Hubble sphere for where recession velocity currently equals light speed. None of them are walls in any physical sense. None of them mark a place where space ends or changes character. All of them are boundaries defined by the relationship between the speed of light and the dynamics of expanding space, and all of them have something important in common. They are all far smaller than the universe. We know this. We know it not because we have sent probes to the edge and looked beyond, but because the physics that produced our universe leaves unmistakable fingerprints inside it. Fingerprints that point outward past every boundary we can measure toward a structure so much larger than our observable sphere that the comparison makes the comparison between a single atom and the observable universe seem like a reasonable analogy. And understanding how we know that, understanding the mechanism that built these boundaries and simultaneously built us, requires going back much further than Hubble. It requires going back to the first fraction of the first second of the universe's existence, to a moment so brief and so violent that the human capacity for analogy nearly fails in trying to describe it. It requires going back to inflation. But before we get there, it is worth sitting for just a moment longer with what we have established, because there is something that deserves to be felt rather than merely understood. You are located at the exact center of the observable universe, not approximately the center, not near the center, the geometric center. Every observer in the cosmos is at the center of their own observable sphere, because every observer's sphere is defined by the distance light has had time to travel since the universe became transparent, and that distance is the same for every observer, regardless of where they are. An alien civilization in a galaxy, near what we perceive as our observable edge, has its own sphere centered on itself, extending equally in all directions from its own position. Their sky contains 2 trillion galaxies we will never see in directions. We cannot look at distances that no signal of ours will ever reach. They are not in a privileged position, neither are we, neither is anyone. Every observer in the universe is, by the physics of observation, in an expanding space-time, necessarily at the center of their own bubble of visibility. And that bubble for all of us is only a small window onto something much, much larger. The window has a back wall. That wall is made of light, the oldest light in the universe. The light that was released when the cosmos was 380,000 years old and first became transparent to radiation. Before that moment, the universe was a plasma, a dense hot fog of charged particles so thoroughly interwoven with photons that light could not travel freely. Every photon was absorbed and re-emitted, almost immediately unable to make progress in any direction. The universe was opaque, the way the interior of the sun is opaque, not because there is anything blocking the view from outside, but because the medium itself is so dense that light cannot pass through it coherently. Then, as the universe expanded and cooled, something changed. The temperature dropped to roughly 3000 Kelvin, cool enough for electrons and protons to combine into neutral hydrogen atoms. And neutral hydrogen, unlike a plasma of free charges, is largely transparent to radiation. In what cosmologists call recombination, though, the word is something of a misnomer, since the electrons and protons had never been combined before the universe became transparent. Photons that had been trapped in the plasma were suddenly free to travel. They have been traveling ever since, and they are arriving here right now from every direction as the oldest electromagnetic signal the universe contains. We call this signal the cosmic microwave background. We can detect it with radio telescopes tuned to the right frequency, and when we map it across the sky, we see a nearly perfect glow at a temperature of 2.725 Kelvin, just barely above the coldest temperature anything can ever reach. The small variations in that temperature, fluctuations of roughly 1 part in 100,000, are the seeds of everything that exists. The slightly denser regions in that ancient plasma became over billions of years of gravitational collapse. The galaxies and clusters of galaxies we see today. The slightly less dense regions became the vast cosmic voids between them. The cosmic microwave background is not the edge of the universe. It is the edge of our line of sight, using electromagnetic radiation. Beyond it, in every direction, space continues. It continued before the universe became transparent as that opaque plasma, and it continued after inflation stretched regions far beyond any boundary we can ever reach using light. It is in the most precise sense the back wall of our window, and staring at it, measuring it, reading its temperature fluctuations to fractions of a millionth of a degree is how we know what we know about the universe's infancy and about the mechanism that built both us and our boundaries. The wall is ancient. It has been sitting there radiating its faint microwave glow for 13.8 billion years, and encoded in it, in the precise statistical pattern of its temperature variations, is the answer to the question we have been building toward since the first words of this video. Why is the universe the shape it is? Why is the geometry of space flat to within 0.5% across a sphere, 93 billion light-years in diameter? Why is the temperature of the cosmic microwave background uniform to 1 part in 100,000 across regions of the sky that should by any reasonable calculation have had no opportunity to interact with each other and reach thermal equilibrium? Those questions have one answer, and that answer is the most consequential piece of physics in this entire story, because it simultaneously explains our existence and explains our ignorance. It tells us why we are here and why we cannot see most of what is here with us. There is a number at the center of this story, not a large number in the way that 2 trillion galaxies is a large number, not a figure that impresses through sheer magnitude, but a number that disturbs through precision. A number whose value, when you follow its implications carefully and without flinching, reveals something about this universe that sits just at the edge of what physics can explain. The number is called omega, and omega describes the shape of everything. Not the shape of a galaxy, not the shape of a supercluster, not even the shape of the observable universe in the conventional sense. Omega describes the overall curvature of space itself, the geometry of the cosmos at the largest scale any measurement can reach. It is defined as the ratio of the actual density of the universe to a specific critical density, the density at which the universe is perfectly flat. If omega equals exactly 1 space is flat, Euclidean geometry applies at the largest scales. Parallel lines stay parallel forever. The angles of a triangle sum to exactly 180 degrees no matter how large the triangle is drawn. If omega is greater than 1 space curves back on itself like the surface of a sphere. Parallel lines eventually converge. Triangles have angles that sum to more than 180 degrees. The universe is finite and closed. If omega is less than 1, space curves outward like the surface of a saddle. Parallel lines diverge. Triangles have angles summing to less than 180 degrees. The universe is open and infinite in a specific geometric sense. When the Planck satellite, the most precise cosmic measurement instrument humanity has ever constructed, completed its survey of the cosmic microwave background and returned its final data, the value it recorded for omega was 1.0, 00 plus or minus 0.005. The universe is flat, not roughly flat, not approximately flat, flat to within 0.5% measured across a sphere 93 billion light-years in diameter. Sit with that for a moment before moving on. 93 billion light-years. A single light-year is approximately 5.88 trillion miles. Multiply that by 93 billion, and you have a number so large that writing it out in standard notation would require more digits than there are atoms in a human body. Across that entire expanse, across a volume of space so enormous that no sensory experience available to a human being can form an adequate picture of it, we have measured the geometry of reality and found it balanced on a knife edge to within 0.5%. That should bother you, not in a frightening way, in the way that a magic trick bothers you when you cannot figure out how it was done. Because here is what that precision actually means when you look at it through the equations of general relativity. Flatness in cosmology is not a stable condition. It is not the natural resting state that space settles into over time the way water settles to the bottom of a container. It is precisely the opposite. In the equations that govern the evolution of the universe, omega equals 1 is what mathematicians call an unstable fixed point. It is a balance point that the universe will not stay near unless it was placed there with extraordinary precision and is kept there by some mechanism. Without such a mechanism, any deviation from flatness, however small, grows over time. The universe evolves away from flatness, not toward it. The analogy that captures this most vividly is a pencil balanced vertically on its tip. You can achieve that balance for a moment with extraordinary care, but the equilibrium is unstable. The slightest perturbation, a vibration in the table, a breath of air, a fluctuation too small to measure, will send the pencil falling. And the longer time passes after that initial nudge, the further from vertical the pencil gets. The deviation does not stay small, it grows. The universe works exactly this way. If omega had started even slightly above 1 in the very early universe, the self-gravity of everything in existence would have been just strong enough to overcome the expansion. Space would have reached a maximum size and then collapsed back inward, ending in what cosmologists call the Big Crunch. The timescale for this collapse depends on how far above 1 omega started. If the deviation was large, the collapse would have been swift. A universe that expanded for perhaps a few 100,000 years, never forming a single star, before folding back on itself into a singularity. If the deviation was small, the collapse might have taken longer. But in either case, no stars, no planets, no carbon, no observers of any kind. And if omega had started slightly below 1, the opposite catastrophe. Expansion would have won decisively and permanently. Space would have stretched apart so quickly that the matter within it never had the opportunity to clump together under gravity. You would have ended up with a universe of thinning, cooling gas spreading outward forever into a featureless dark expanse. No gravitational collapse, no stars igniting, no nuclear furnaces fusing hydrogen into the heavier elements that chemistry requires. No you sitting wherever you are contemplating any of this. The window between these two outcomes is extraordinarily narrow, and here is where the number becomes genuinely staggering, where it crosses from impressive precision into something that feels like it should not be possible. For omega to be as close to 1 as Planck measured it today, for the universe to be this flat at this moment, in its 13.8 billion year history, the value of omega, at the very beginning, at what physicists call the Planck time, 10 to the power of negative 43 seconds after. The origin of the universe would have had to equal 1 to within 1 part, in 10 to the power of 62. Write that out. 1 followed by 62 zeros in the denominator. That is the precision to which the initial conditions of the universe needed to be set for you to exist. If the initial value of omega had differed from 1 by even a single unit in the 62nd decimal place, the universe would have either collapsed or dispersed long before a single star ever ignited, before any planet ever formed, before any chemistry ever occurred, before any process capable of producing something that could ask why had any opportunity to begin. This is the flatness problem, and calling it a problem is a significant understatement. It is not the kind of problem where you shrug and say the universe just happened to start that way, as if it were a minor coincidence requiring no explanation. Saying the universe just happened to start with omega equal to 1 to within 1 part in 10 to the 62nd is like saying a bullet fired from a rifle a billion light years away just happened to pass through the eye of a needle in front of you. You could say it. The probability is not 0, but the reasonable response is not to accept it. The reasonable response is to look for the mechanism that aimed the rifle. The flatness problem is not a puzzle about measurements being imprecise or models being incomplete. It is a puzzle about initial conditions, about why the universe started in a configuration so precisely calibrated that its subsequent evolution produced a cosmos capable of containing anything complex at all. And in standard Big Bang cosmology, the cosmology without any additional mechanisms, without inflation, there is no answer. There is no known physical process, no symmetry, no conservation law, nothing in the equations of general relativity or quantum field theory that would naturally drive omega toward exactly 1. It is simply assumed. It is placed there by hand as an initial condition with no justification for its extraordinary precision other than the observation that if it were otherwise, we would not be here to notice. That last statement is what philosophers of science call an anthropic argument. The universe must have had properties consistent with the existence of observers because we are here observing it. This is logically true. It is also on its own deeply unsatisfying. It explains the observation without explaining the mechanism. It tells you that the rifle was aimed, but not by what or how. And physics at its best is the search for mechanisms. The flatness problem does not stand alone. It is part of a cluster of related problems, independent puzzles that arise when you take standard Big Bang cosmology without any additional ingredients and follow it to its logical conclusions. Each of them points from a different direction at the same gap in our understanding, and together they make a specific kind of demand on physics, the demand for a mechanism operating in the very early universe that is unlike anything in ordinary cosmological evolution. The second problem is the horizon problem, and it is in some ways even more striking than the flatness issue, because it is visible directly in the data we have been discussing. The cosmic microwave background, the ancient light released when the universe was 380,000 years old, is uniform in temperature across the entire sky to 1 part in 100,000. Not approximately uniform, not mostly uniform with some large-scale variations. Uniform to 4 decimal places in every direction across the full 360 degrees of sky. The temperature in one direction is 2.725 Kelvin. The temperature in the diametrically opposite direction is also 2.725 Kelvin to within a few hundred thousandths of a degree. This would be unremarkable if the regions of the early universe responsible for that light in those 2 opposite directions had been in thermal contact. If they had been close enough that heat could flow between them, that photons could travel from one to the other and bring them to a common temperature, the way a cup of hot coffee and a glass of cold water placed next to each other will eventually reach the same temperature if you wait long enough. Equilibrium is the natural outcome of thermal contact. It is expected and unremarkable, but those 2 regions were not in thermal contact. In standard Big Bang cosmology without inflation, the region of the early universe that produced the CMB light we see in one direction of the sky, and the region that produced the CMB light in the opposite direction had never been in causal contact. The distance between them at the time the CMB was emitted was larger than the distance light could have traveled since the beginning of the universe. No signal, no photon, no influence of any kind could have passed between them. They had been causally isolated since the very beginning, and yet they are at the same temperature. The analogy is placing a cup of hot coffee and a glass of cold water on opposite ends of a table that stretches for 1,000 light years, and finding when you check them later that they have reached identical temperatures. The only explanation in standard physics is that they started at the same temperature, but that merely pushes the question back one step. Why would causally disconnected regions start at the same temperature? There is no mechanism in standard Big Bang cosmology that would produce this outcome. It is like the flatness problem, an assumed initial condition with no physical justification. Cosmologists estimate that the observable CMB sky is composed of approximately 100,000 causally disconnected patches, 100,000 regions that in standard cosmology had no opportunity to exchange information or energy before they emitted the light we observe today. All of them are at the same temperature to 4 decimal places. The probability of this occurring by coincidence, by the random accident of independent initial conditions, all landing on the same value, if it is so small that expressing it as a number provides no useful intuition, it is in practical terms impossible, and yet the data is unambiguous. The third problem, the monopole problem, is slightly more technical in its origins, but no less troubling in its implications. In the extreme heat of the very early universe, temperatures so high that the energies involved dwarf anything unachievable in the most powerful particle accelerators humanity has built, the fundamental forces of nature are believed to have been unified. At low energies, the world has 4 distinct forces: gravity, electromagnetism, the weak nuclear force responsible for radioactive decay, and the strong nuclear force that binds atomic nuclei together. But grand unified theories, the class of theoretical frameworks attempting to unify 3 of those 4 forces into a single description, predict that at the temperatures of the very early universe, they were indistinguishable. One force, one description. As the universe cooled, That unified force underwent what physicists call a phase transition, a change analogous in some ways to water freezing into ice, but occurring in the fabric of the fundamental fields of physics rather than in the arrangement of molecules. And phase transitions in physics produce defects. When ice forms quickly from supercooled water, it crystallizes in multiple places simultaneously, and where the growing crystals meet, their different orientations produce grain boundaries, structural imperfections in the ice. Grand unified theories predict that the phase transition of the early universe produced analogous defects in the fabric of spacetime itself. These defects are called magnetic monopoles, hypothetical particles carrying a single magnetic pole, either north or south, but not both, unlike every magnet we have ever observed which always has two poles. The predicted density of magnetic monopoles produced in the early universe under standard Big Bang cosmology is enormous. There should be roughly one monopole per cubic centimeter of space. If that were true, the universe would be so dense with magnetic monopoles that their combined mass would have halted the expansion of the universe almost immediately after the Big Bang. We would not be here. And even setting aside their gravitational effects, we should find magnetic monopoles everywhere. In every rock, in every cubic meter of seawater, in every detector we have ever built, we have never found one. Not a single magnetic monopole has been detected, despite decades of dedicated searches using sensitive instruments designed specifically to detect them. 3 problems. The flatness problem demanding that the initial conditions of the universe be set to a precision of 1 part in 10 to the 62nd, with no explanation for why. The horizon problem requiring that causally disconnected regions of the early universe be at the same temperature with no mechanism to explain the equilibrium. The monopole problem predicting a universe so dense with exotic particles that it should have collapsed immediately, yielding instead a cosmos where those particles appear to be completely absent. In the winter of 1979 and 1980, a young particle physicist named Alan Guth was working at Stanford University on a problem that was in his own description merely technical. He was not thinking about the deep philosophical puzzles of cosmology. He was thinking about the specific prediction of grand unified theories regarding magnetic monopoles and why the universe contained none of the things those theories predicted should be everywhere. It was a narrow, concrete problem. The kind of problem a careful theoretical physicist works on because it has a clear statement and might have a clear answer. What Guth found was not a narrow answer. What he found, according to his own research notes from that period, was what he recorded as a spectacular realization. A mechanism that solved the monopole problem, yes, but simultaneously and by the same operation solved the flatness problem and the horizon problem. A single physical process that resolved 3 independent paradoxes with one stroke. He called it inflation. The mechanism is this. In the very early universe, the dominant energy was not matter or radiation. It was the energy of a quantum field, what Guth modeled as the energy associated with a phase transition in grand unified theories, a field that was stuck in what physicists call a false vacuum. A false vacuum is a state that is locally stable but not at the lowest possible energy. Think of a ball resting in a shallow depression partway up a hill. The ball is stable for the moment. It is not rolling, but it is not at the bottom of the hill either, not at the minimum energy state. If it receives a sufficient kick, it will roll over the rim of its local depression and down to the valley below to the true vacuum, the actual minimum. While the inflaton field, as it is now generically called, was trapped in this false vacuum, it had a peculiar and consequential property. It acted like a cosmological constant, a form of energy that permeated all of space uniformly and did not dilute as space expanded. Unlike matter, which spreads out and becomes less dense as the volume it occupies increases, unlike radiation, which does the same and also loses energy to redshifting, the energy of the false vacuum maintained its density regardless of how much space expanded. It was a constant energy density of empty space itself. This constant energy density in the equations of general relativity produces a specific and dramatic effect. It drives exponential expansion, not the ordinary expansion of space that has been occurring for the last 13.8 billion years, which is expansion where the rate slows over time as the energy density decreases. Exponential expansion means space doubles in size in some fixed short time interval, then doubles again in the same interval, then doubles again. The doubling time under inflation was something like 10 to the negative 37 seconds. In 10 to the negative 36 seconds, inflation doubles space 10 times, growing it by a factor of roughly 1,000. In 10 to the negative 35 seconds, 100 doublings a growth factor of 10 to the 30th. The total expansion factor from inflation under the most conservative models consistent with the CMB data is at minimum around 10 to the 26th. 10 to the 26th. Let that settle into place through an analogy rather than just as a number. Take a single hydrogen atom. The nucleus of a hydrogen atom, a single proton, has a diameter of about 1 femtometer 10 to the negative 15 meters. It is invisible not just to the naked eye, but to any optical microscope ever built, smaller than the wavelength of visible light by a factor of roughly 1,000. If you inflated that proton by a factor of 10 to the 26th, expanding it at the inflationary rate for the duration of the inflationary epoch, it would end up larger than the entire observable universe. Larger than the sphere 46.5 billion light-years in radius, containing 2 trillion galaxies, and every photon that has ever reached our instruments. That is what inflation did to space. The region that became our observable universe was before inflation smaller than a proton. After inflation, it became enormously larger than the observable universe, with the observable universe being just a tiny patch of the inflated volume. And here is how this solves simultaneously all 3 problems. The flatness problem first. Before inflation, the region that would become our observable universe was small, so small that whatever initial curvature it had was significant. Omega was whatever it was, probably not particularly close to 1, set by whatever physical processes governed the pre-inflationary epoch. But then inflation stretched this tiny region by a factor of at least 10 to the 26th. Recall the analogy of standing on a sphere. On a basketball, the curvature is obvious. On the Earth, it is imperceptible. On an object 10 to the 26th times larger than the Earth, it would be so small as to be utterly undetectable by any instrument we could build. Inflation does not require omega to have started at exactly 1. It takes whatever starting value omega had and drives it exponentially close to 1 by stretching space so enormously that any initial curvature becomes geometrically negligible. The flatness we observe is not a coincidence. It is a consequence. The horizon problem next. Before inflation, the region that would become our entire observable universe was small enough, smaller than a proton, that all of it was in causal contact. Light could cross it. Heat could equilibrate. Every part of it could interact with every other part and reach the same temperature. Then, inflation stretched this already equilibrated region into something vastly larger than what we can observe. The cosmic microwave background is uniform because the entire observable universe was before inflation a single causally connected region that had already thermalized. The uniformity is not a coincidence. It is a fossil, a preserved record of a pre-inflationary equilibrium stretched to cosmic scales. The monopole problem last. If magnetic monopoles were produced by phase transitions before or during the early stages of inflation, then the subsequent exponential expansion would have stretched the volume of space so enormously that the density of monopoles would have dropped to essentially 0 within our observable sphere. Inflation dilutes them into irrelevance. 1 monopole per cubic centimeter becomes 1 monopole per volume of space so large that the expected number within our entire observable universe rounds to 0. The absence of monopoles is not evidence against grand unified theories. It is evidence for inflation. 3 problems, 1 mechanism. This convergence is the reason inflation is taken seriously by the majority of working cosmologists. It is not one solution to one problem which might be coincidence, a mathematical trick that happens to fit one dataset. It is one solution to 3 independent problems simultaneously, each pointing from a different direction at the same mechanism. That is the signature of something real. But here, as we keep returning to because we must, is the cost. Every solution in physics has a price. Conservation laws are balanced. You cannot get something from nothing without the equations telling you exactly what you gave up. And the price of inflation is the thing that this entire journey has been building towards since its opening sentence. If inflation stretched the region that became our observable universe by a factor of at least 10 to the 26th, it did not stop neatly at the edge of what would later become visible to us. It stretched everything. It stretched the regions of space that were before inflation in causal contact with our region. Regions that shared the same pre-inflationary equilibrium, the same initial conditions, the same early history. And it pushed them so far away that no signal traveling at the speed of light through any amount of time the universe will ever have will ever reach us from them. The observable universe, 46.5 billion light-years in radius, 2 trillion galaxies, 13.8 billion years of visible history, is not the universe. It is the tiny patch that happened to fall within our causal bubble after inflation expanded the pre-inflationary region to scales that dwarf everything we can see. Everything beyond our horizon is not nothing. It is more of this. More space, more galaxies, more stars, more history, more complexity. All formed by the same physics from the same initial conditions, all permanently invisible, because inflation placed them beyond the reach of any signal we could ever send or receive. The solution and the concealment are the same event. The mechanism that allowed complexity to exist is the mechanism that hid most of reality from the only observers capable of noticing. And the question of how much reality was hidden, how much lies beyond the boundary that inflation built into the structure of space-time, is the question we will spend the next chapter quantifying. Because the number, when you actually calculate it, is not merely large. It is the kind of large that requires a new relationship with the concept of scale entirely. In 2011, three cosmologists published a paper that attempted to answer a question deceptively simple in its phrasing but staggering in its implications. The question was this: given everything we currently know, given every measurement from every instrument humanity has ever pointed at the sky, given the full suite of data from Planck and WMAP and the galaxy surveys and the supernova observations, what is the minimum size the actual universe could be? Not the observable universe, not the causal bubble defined by inflation and the speed of light. The actual universe, the full extent of space as far as it goes, whether or not any of it is visible to us. Miran Vardanyan, Roberto Trotta, and Joseph Silk approached this question using a statistical framework called Bayesian model comparison. The name sounds technical, and the mathematics behind it is genuinely sophisticated, but the core idea is straightforward. You take a set of competing hypotheses about the size and geometry of the universe. You ask which hypothesis is best supported by the available data, applying a penalty for hypotheses that require many adjustable parameters to fit the observations. You are not simply asking which model fits the data best, because a model with enough free parameters can fit any data. You are asking which model explains the data most efficiently with the fewest assumptions. It is a rigorous way of balancing explanatory power against theoretical economy. Vardanyan, Trotta, and Silk fed the Planck flatness measurement into this framework, along with the full set of cosmological observations, and they asked what minimum size was required for each geometric model to be consistent with what observe. The answer they arrived at has been sitting in the published literature for over a decade, cited by subsequent analyses, and it has not diminished in its impact with familiarity. The universe must have a radius at least 251 times the radius of the observable universe. 251 times 46.5 billion light-years. That gives a minimum radius of approximately 11.7 trillion light-years, and volume scales as the cube of the radius. 251 cubed is approximately 15.8 million. The minimum volume of the actual universe, under this conservative analysis, using the most mainstream cosmological data available, is roughly 15.8 million times the volume of our observable sphere. 15.8 million observable universes, minimum. There are approximately 2 trillion galaxies in our observable universe. Multiply by 15.8 million. The minimum number of galaxies in the actual universe under this conservative lower bound estimate is approximately 32 sextillion. That is 32 followed by 21 zeros. 32,000 billion galaxies, every single one of them invisible to us, every single one of them governed by the same physics, seeded by the same inflationary quantum fluctuations formed by the same gravitational collapse over the same 13.8 billion years of cosmic history. They are not exotic objects in some alien physics. They are, statistically speaking, much like the galaxies we do see. Ordinary, invisible, permanently inaccessible. Let that number settle for a moment through the lens of human time rather than human space, because spatial scales of this magnitude have ceased to carry intuitive weight. If you tried to count those 32 sextillion galaxies at the rate of 1 per second without pausing, without sleeping, without stopping, for any reason the counting would take approximately 1 trillion years. The current age of the universe is 13.8 billion years. You would need to count for roughly 70 times the current age of the universe to reach the minimum number of galaxies that the actual universe contains, accounting only for what lies beyond our observable sphere. And that is the conservative number. That is the floor. The minimum consistent with the simplest inflationary models applied to the most constrained interpretation of the Planck data. The actual number under models where inflation lasted slightly longer or began from initial conditions slightly further from flatness is vastly larger. Many well-motivated inflationary models predict expansion factors not of 10 to the 26th, but of 10 to the hundreds or 10 to the thousands. Under those models, the ratio of the actual universe to the observable universe is not 15.8 million to 1. It is a number for which no analogy drawn from human experience provides any foothold whatsoever. And then there is the possibility that the universe is not merely very large, but genuinely mathematically infinite. An infinite universe is not simply a very large one. It is categorically different. A very large universe has a size, even if that size exceeds any practical means of expression. An infinite universe has no size. It extends without limit in every direction with no boundary, no edge, no furthest point. And if the universe is infinite and filled with matter distributed roughly uniformly on the largest scales as our observations of the observable portion suggest it is, then the implications are not merely large. They are in the strict logical sense absolute. In an infinite universe, every possible arrangement of matter and energy that is physically permissible will be realized. Not occasionally, not rarely, infinitely many times. Because there are only finitely many ways to arrange the matter and energy within any finite volume, however large, and an infinite universe contains infinitely many such volumes. The number of distinct quantum states available to a volume the size of our observable universe is enormous but finite. Quantum mechanics places an upper limit on the information content of any finite region of space. That limit, connected to the holographic principle we will return to later, means that the number of distinguishable configurations of our observable universe is large but bounded. In an infinite universe, a bounded number of configurations distributed across an infinite volume means every configuration repeats, not once, infinitely many times, including inevitably a configuration identical to the one we occupy right now. A Milky Way galaxy orbited by a solar system on whose third planet a species of curious primates evolved, some of whom built telescopes and particle accelerators and wrote papers about Bayesian model comparison, and one of whom is at this moment watching a video about the size of the universe. The distance to the nearest exact copy of our observable universe in an infinite flat cosmos has been calculated. The cosmologist Max Tegmark performed this estimate working from the number of possible quantum states in a volume the size of our observable sphere. The answer is approximately 10 to the power of 10 to the power of 118 meters, a number so large that it cannot be visualized, barely can be written, and certainly cannot be traveled in any universe with a finite speed of information. Yet, in an infinite universe, it is not infinite. It is a finite distance. The nearest copy of you thinking exactly the thoughts you are thinking right now is 10 to the 10 to the 118 meters away, unreachable, real, required by the mathematics. This is not mysticism. This is not a philosophical speculation dressed up in the language of physics. It is the direct, logical consequence of combining an infinite universe with the observed uniformity of the CMB, the known laws of quantum mechanics, and the finite information content of any bounded region of space. If you accept those three things, the repetition follows as inevitably as any conclusion in mathematics. We do not know whether the universe is infinite. What we know is that it is at minimum vastly larger than anything we can see, and that the physics we understand offers no mechanism to prevent it from being infinite. Infinity is the default outcome of a flat universe extending beyond any boundary we have identified, and flatness to the precision Planck measured it is what we have. But flatness does not tell you everything about the universe's shape. This is the place where a distinction enters the story that most people have never encountered, a distinction that changes what it means to ask how large or what shape the universe is. It is the distinction between geometry and topology. Geometry describes the local curvature of space. It answers questions about what happens between two nearby points. Do parallel lines stay parallel? Do the angles of a triangle add up to 180 degrees? Is the shortest path between 2 points a straight line? These are geometric questions, and the Planck measurement answers them. The geometry of our universe is flat Euclidean to within 0.5% across the full extent of our observable sphere. Topology describes the global shape. It answers questions about what happens if you keep traveling in one direction for a very long time. Does space extend forever, or does it eventually loop back on itself? Is there a boundary, or does the universe fold in a way that makes it finite without having an edge? These are topological questions, and crucially, they are independent of the geometric questions. The same local geometry, the same flatness, the same Euclidean rules for triangles and parallel lines is compatible with many different global topologies. The clearest way to see this is through a two-dimensional analogy that makes the abstract concrete. Take a flat piece of paper. Locally, it is perfectly flat. Every triangle drawn on it has angles summing to exactly 180 degrees. Parallel lines stay parallel. The geometry is Euclidean in every neighborhood. The simplest topology for this flat surface is the infinite plane extending forever in every direction. But there is another topology that is equally flat locally. Take that same flat piece of paper and connect the left edge to the right edge. You get a cylinder. Every small triangle on the cylinder's surface still has angles summing to 180 degrees. The local geometry is unchanged, but the global topology is now different. If you travel far enough in one direction, you return to where you started. Now take the cylinder and connect its two circular ends, bending it until they meet. What you get is a torus, the surface of a donut shape. And here is the remarkable thing. That surface is still locally flat. The curvature that you can see in the donut shape as an object in three-dimensional space is what mathematicians call extrinsic curvature, the way the surface bends through the higher dimensional space it is embedded in. But the intrinsic geometry of the surface, the geometry experienced by a creature living on it and drawing triangles and measuring angles, is still perfectly Euclidean. Small triangles still sum to 180 degrees. Parallel lines drawn locally still stay parallel locally. And yet if you start walking in a straight line and keep going, eventually you come back to where you started. The surface is finite. It has no edge, and it cannot be distinguished from an infinite flat plane through any local geometric measurement. Extend this to 3 dimensions, and you have what mathematicians call a three-torus, or hypertorus. Imagine a cube. Identify the left face with the right face, meaning that anything traveling through the right wall reappears through the left. Identify the top face with the bottom face, so that anything traveling upward through the ceiling reappears through the floor. Identify the front face with the back face, so that anything passing through the front wall enters from the back. The resulting space is locally flat. Every local geometric measurement satisfies Euclidean rules consistent with what Planck measured. But globally, the space is finite and connected in a looping way. Travel far enough in any direction, and you return to your starting point. There is no center, no edge, no special location, just space that wraps around on itself at some vast scale. If you have ever played the original Pac-Man moving off the right side of the screen and reappearing on the left, you have experienced a two-dimensional version of this topology. A hypertorus is that in all three spatial dimensions simultaneously. This possibility was taken seriously by some of the most distinguished cosmologists of the 20th century. Yakov Zeldovich and Alexei Starobinsky, both central figures in Soviet cosmology, explored the implications of a topologically non-trivial universe in the 1970s and 1980s. Starobinsky, who developed one of the most successful models of cosmic inflation, still favored by observational data, found the idea worth serious mathematical investigation. These were not peripheral figures entertaining speculative ideas at the margins. They were among the most rigorous theoretical minds the field has produced. The reason topology matters observationally is precise and testable. If the universe is a hypertorus with a topological identification scale comparable to or smaller than our observable sphere, then we would be looking at the same physical regions of space from multiple directions. Looking out in one direction, we see a particular patch of the early universe imprinted on the CMB. Looking in a different direction, we see the same patch approached from the other side of the loop. The temperature pattern of the CMB in those two directions would be identical, not statistically similar in the way that nearby random patches are similar, but identical to the precision of the measurement because it is the same physical region viewed from two different angles. What you would find if you knew how to look is pairs of circles on the CMB sky where the temperature pattern matches exactly. The same arrangement of hot and cold spots rotated or reflected, depending on the geometry appearing in two different parts of the sky. Cosmologists call these matched circles, and they are the definitive observational signature of a finite topologically connected universe. The Planck satellite looked for them. Its topology analysis, published in 2015, searched the CMB sky systematically for matched circle pairs across a wide range of angular scales and geometric configurations. It found none. But here is where the result requires careful interpretation, because a non-detection in science is not the same as a refutation. What Planck's search tells us is not that the universe has no topology. It tells us that if the universe is a hypertorus, the topological identification scale must be larger than approximately 1.2 times the diameter of our observable sphere. The loops, if they exist, are too big to produce matched circles within the portion of the CMB we can observe. The signature would be there in principle, but sitting just beyond our horizon in a region of the CMB we cannot access, because it corresponds to distances beyond our causal boundary. In other words, a topologically finite universe is entirely consistent with the Planck data, as long as the topology operates at a scale larger than our observable sphere. And given what inflation almost certainly did to spatial scales, stretching everything by at least a factor of 10 to the 26th, a topological identification scale larger than our observable sphere is exactly what inflation would produce, even if the pre-inflationary universe had a compact topology. Inflation stretches topology along with everything else. If space looped back on itself before inflation at some small scale, inflation would have stretched that loop to scales vastly exceeding our observable bubble, making it permanently undetectable from inside. The two ideas, inflation and compact topology, are not in tension, they coexist comfortably. A universe could be simultaneously the product of inflation, geometrically flat to the Planck precision, and globally finite, with a hypertorus or more exotic topology, and we would have no observational way of distinguishing it from a genuinely infinite flat universe. Both would look identical from inside our causal bubble. There are topological possibilities more exotic than the hypertorus that have attracted serious attention. The Poincare dodecahedral space is a finite, three-dimensional space constructed by identifying opposite faces of a regular dodecahedron, a 12-sided polyhedron with a specific rotation. It has the peculiar property of producing very specific, matched circle patterns in the CMB, not just any circles, but circles with a particular angular size determined by the geometry. In 2003, Jean-Pierre Luminet and colleagues published a paper in Nature arguing that this topology provided a better fit to the large angle anomalies in the WMAP CMB data than an infinite flat model. The paper attracted enormous attention and generated a substantial literature of responses, analyses, and independent tests. The consensus that eventually emerged was that the evidence was not statistically compelling enough to confirm the model, and subsequent Planck searches did not find the predicted match circle pattern at the expected angular scale. But the anomalies that motivated the investigation did not disappear with the Poincaré model. They remain in the Planck data, sitting quietly and persistently. The large angle anomalies of the CMB deserve attention in their own right, because they represent one of the most carefully studied puzzles in modern observational cosmology. When you decompose the CMB temperature pattern into its component modes at different angular scales, the mathematical equivalent of breaking a musical chord into its individual notes, you find a hierarchy of structures. The largest scale components, the quadrupole and the octupole, describe the broadest temperature variations across the sky. In a universe whose initial conditions were generated by inflation, a process isotropic by nature, with no preferred direction in space, these large-scale components should be statistically independent of each other and of any structure in our local cosmic neighborhood. They should point in random directions uncorrelated with the plane of Earth's orbit around the Sun, uncorrelated with the plane of the Milky Way, uncorrelated with each other. They are not. The quadrupole and the octupole are aligned with each other to a degree that is statistically improbable in a purely random field. More striking still, both are aligned with the ecliptic plane, the plane of Earth's orbit around the Sun. The probability of this alignment occurring by chance in a genuinely isotropic universe is less than 1%. The anomaly was found in WMAP data and confirmed independently by Planck. It has persisted across multiple independent analyses using different foreground removal methods. It was given the name the axis of evil, a label that has endured partly for its drama and partly because it captures the genuine discomfort the anomaly produces in cosmologists, who take seriously the principle that the universe should have no preferred direction on its largest scales. The natural first response is foreground contamination. Emission from within our own solar system and from the Milky Way's plane could naturally correlate with the ecliptic and galactic coordinates. Cosmologists have worked carefully to subtract these foregrounds using multiple independent techniques. The anomaly is reduced by foreground removal. It is not eliminated. It persists at a residual level across cleaned maps produced by different groups using different methods. Whether the residual represents a systematic artifact that no current analysis has quite managed to model correctly, or a genuine feature of the primordial CMB, is unresolved. But it sits there in the data, one of several smudges on the otherwise extraordinary agreement between observation and the standard cosmological model. There is something worth sitting with in all of this. In the topology story, in the large angle anomalies in the match circle, searches that found nothing but constrained rather than refuted, we are watching physics push up against its own boundaries. We are watching a field that has built instruments of extraordinary precision, that has measured the temperature of the oldest light in the universe to fractions of a millionth of a degree, discover that some of its most fundamental questions cannot be answered by any instrument it could ever build. Not because the instruments are imperfect, because the answers, if they exist, are beyond the causal horizon that inflation established. The topology of the universe, its global shape, whether space is infinite or finite and folded, is in principle determined by physics. There is an answer. The universe either wraps back on itself or it does not. If it does, the identification scale is either within our observable sphere, in which case Planck would have found the matched circles, or it is beyond our sphere, in which case no observation we can make will ever determine it directly. We are in the second situation. We know we are. And this means that one of the most basic questions you could ask about the thing you are embedded in its overall shape is permanently beyond the reach of empirical determination from our location in space-time. That is not a failure of science. It is a result of science, a hard-won, precisely quantified understanding of the limits of what can be known from inside a causal bubble in an inflated universe. The boundary of knowability has been located with precision, and locating it, understanding exactly why it sits where it sits and what placed it there, is itself a profound piece of knowledge about the structure of reality. The universe is at least 251 times larger than what we can see. It may be infinite. Its global topology is unknown and may be unknowable. Every galaxy within our observable sphere is accompanied by at minimum 15.8 million invisible counterparts beyond our horizon, formed by the same physics, governed by the same laws, permanently beyond the reach of any signal we could send or receive. And the reason for all of this, the reason the boundary sits where it sits, the reason the topology is inaccessible, the reason the minimum size is the minimum, traces back to a single event, lasting less than 10 to the negative, 32 seconds in the first fraction of the universe's first moment. Inflation did not merely solve 3 problems in cosmology. It wrote the terms of our permanent ignorance into the structure of space-time itself. The question now is what it is still doing. Because inflation in the most complete versions of the theory did not simply happen once in our past, producing our universe as a single outcome, the mathematics followed carefully suggests something far stranger. Something that has been called eternal. Something that turns our observable universe, 2 trillion galaxies, 13.8 billion years of history, 46.5 billion light-years of depth, into something that barely registers as a rounding error in the full account of what inflation produced. The mathematics of inflation does not stop where inflation stops. That sentence requires unpacking because it is easy to hear it as a vague philosophical gesture toward incompleteness, as a way of saying that our models have loose ends. It is not that. It is a precise technical statement about what happens when you take the quantum mechanics that inflation requires to produce the density fluctuations we observe in the CMB, and you follow those quantum mechanics to their logical conclusion without imposing any artificial boundary on the calculation. When you do that, without flinching, without deciding in advance that the answer must be tidy, what you find is that inflation, once it begins, does not fully stop. It ends locally in regions like the one that became our observable universe, but it continues elsewhere. It continues always in an ever-expanding volume of space surrounding every local ending, producing new regions, new pockets, new beginnings, without limit and without end. This is called eternal inflation, and understanding why the mathematics insists on it requires going back to the mechanism of inflation itself, to the quantum field at its heart, and to the thing that quantum mechanics does to every field, regardless of what anyone might prefer. The leading class of inflationary models, the ones whose predictions align most closely with the Planck measurement of the CMB spectral index, are called slow-roll inflation models. The name describes the behavior of the inflaton field, the quantum field, whose energy drives the exponential expansion of space. In these models, the inflaton field starts at a high value on its potential energy landscape, the mathematical surface describing how the field's energy varies with its value, and it rolls slowly downward toward the minimum, like a ball rolling down a very gently inclined slope. While it is rolling slowly, its energy is high and approximately constant. That high constant energy is what drives the exponential expansion. Inflation lasts as long as the field is rolling slowly. When the field reaches the bottom of its potential, inflation ends. The field's energy is transferred into the particles of the standard model and the hot dense plasma of the early universe. What we call the hot Big Bang begins. That is the classical picture. A smooth field rolling smoothly down a smooth slope. Inflation preceding, inflation ending, the Big Bang beginning. Clean, sequential, complete. But quantum mechanics does not permit smooth fields. Quantum mechanics imposes fluctuations on every field, always without exception. The uncertainty principle, the foundational constraint of quantum theory, forbids any quantum field from having a precisely defined value at every point in space simultaneously. Every quantum field is subject to constant random fluctuations, tiny quantum kicks that nudge its value up or down around whatever its classical trajectory would be. These are not engineering imperfections. They are not the result of imprecise instruments or incomplete knowledge. They are fundamental features of reality at the quantum level, as certain and unavoidable as the existence of the field itself. In most circumstances, these quantum fluctuations are small, They are perturbations on top of a dominant classical behavior, and while they matter for precise calculations, they do not alter the qualitative outcome. The ball rolls down the hill with small random jiggles superimposed on its smooth descent. The jiggles do not prevent it from reaching the bottom. But here is what Andrei Linde, a Russian-born physicist, then working in the Soviet Union and later at Stanford, realized in the mid-1980s, building on work by Alexei Starobinsky and others. In some regions of inflating space at some moments, the quantum fluctuations will not be small. They will be purely by the random nature of quantum probability, large enough to push the inflaton field back up its potential hill against the direction of classical rolling. Not often, not in most places. But in a universe undergoing exponential expansion, rare events acquire a significance they would not have in a static or slowly growing space. Here is why that matters, and it requires holding two things in mind simultaneously. First, inflation is exponential. Space is doubling and doubling and doubling again on timescales, so short that the numbers barely translate into any human concept of duration. The total volume of inflating space is growing at an extraordinary rate, new space being created constantly, new regions coming into existence in which the quantum field has some value and is subject to quantum fluctuations. Second, in any given region, the probability that a quantum fluctuation kicks the inflaton field back up the hill, delaying the end of inflation in that region, is small, but it is not zero. And in any given time interval, while most regions are evolving classically toward the end of inflation, a small fraction determined by the quantum probability are receiving upward kicks that delay their exit from the inflationary phase. Now combine these two things. The volume of inflating space is growing exponentially. A small but non-zero fraction of that volume is at any moment receiving quantum kicks that extend inflation locally. The number of regions where inflation is being extended is growing because the total volume is growing, and the regions where inflation has been extended continue themselves to expand exponentially, producing yet more volume within which yet more quantum kicks occur, within which yet more regions have their inflation extended. The process is self-reproducing. The total volume of space currently undergoing inflation is not decreasing over time, it is increasing. Inflation is always ending somewhere, producing new regions like ours, where the hot Big Bang begins and matter and radiation evolve into structure. But it is always beginning somewhere else, producing new inflating regions that will themselves eventually end locally, while spawning yet more inflating volume. This is eternal inflation. Not eternal in the past. The question of what preceded inflation is a separate and genuinely open problem, but eternal into the future. Once inflation begins under the quantum mechanics that the standard slow-roll models require, it never stops globally, it terminates locally in pockets. But the background inflationary volume persists and grows forever. Linde worked this out carefully, and what he found was that the condition for eternal inflation is not exotic or specially tuned, it is generic. For the most natural class of inflationary potentials, the ones consistent with the CMB data, inflation is eternal. It does not require any special configuration. It is the default behavior of an inflating universe subject to quantum fluctuations. The question is not why inflation would be eternal, but what would prevent it from being eternal? And the answer to that question in the standard models is nothing. Our observable universe is one of the pockets. One local ending of inflation among what the mathematics suggests is an infinite number of such endings, each one producing a hot, dense plasma that expands and cools into a cosmos of matter and radiation and structure. Our Big Bang was not the beginning of the universe. It was the local end of inflation in our region, the thermalization of inflationary energy into the particles and radiation of our cosmos. A transition, not an origin. In the eternal inflation picture, the structure above and around our pocket is not empty space. It is the inflating background, a volume of space undergoing exponential expansion in every direction, filling in the gaps between the pockets of ended inflation, growing without limit, producing new pockets constantly. The pockets are embedded in the inflationary background, the way bubbles are embedded in boiling water, except the water is expanding exponentially, and will never stop boiling, and the bubbles, rather than rising and bursting, each become their own expanding cosmos. This structure, the foam of pocket universes embedded in an eternally inflating background, is sometimes called the inflationary multiverse. And here is where the picture acquires its most radical and most debated implication. Each pocket universe begins with its own version of reheating, its own local Big Bang, its own initial conditions set by the specific state of the inflaton field in that region at the moment. Inflation ended locally, and those initial conditions are not necessarily identical in every pocket. To understand why, you need to know something about string theory, not its full mathematical architecture, which is intricate and still incomplete, but one specific feature that becomes important here: the landscape. String theory is the leading candidate for a theory of quantum gravity, a framework that attempts to unify general relativity, which describes the large-scale structure of spacetime, with quantum mechanics, which describes the behavior of matter and energy at the smallest scales. It has not been confirmed experimentally, and it faces genuine open questions, but it is the most mathematically developed framework for quantum gravity that exists, and it makes predictions that connect to cosmology in ways that are difficult to ignore. One of those predictions is the existence of an enormous number of possible vacuum states. A vacuum state in quantum field theory is not simply empty space. It is the lowest energy configuration of a particular arrangement of the fundamental fields of physics. Different vacuum states correspond to different values of the physical constants, different strengths of the electromagnetic force, different masses for the electron and the quarks, different values of the cosmological constant, different numbers of large spatial dimensions, different amounts of dark energy built into the fabric of space. In ordinary quantum field theory applied to our universe, there appears to be one vacuum state, the one we inhabit with the physical constants we measure. In string theory, the vacuum is not unique. The theory's mathematical structure admits an enormous number of possible configurations, each corresponding to a different set of physical constants and laws. The number of distinct vacuum states string theory permits has been estimated at approximately 10 to the power of 500. That is not a number that benefits from attempts at analogy. The total number of atoms in the observable universe is roughly 10 to the 80. The string theory landscape dwarfs that by a margin so enormous that the word dwarfs does not begin to capture the relationship. In the eternal inflation picture, when a pocket universe forms and reheating occurs, the inflaton field's energy is deposited into whatever vacuum state that region of space settles into as it cools from the inflationary temperature, and different pockets forming at different times and in different regions of the eternally inflating background may settle into different vacuum states, not because anything unusual is happening, because quantum mechanics governs the transition from the inflationary phase to the reheating phase, and quantum transitions are probabilistic, and in an infinite number of pockets, every vacuum state with non-zero probability will be realized, many of them infinitely many times. What this means is that the other pocket universes, if eternal inflation is correct, are not simply more of our universe placed beyond an unreachable horizon. They are potentially different in their fundamental physics. A pocket universe that settled into a different vacuum state might have a different strength of the electromagnetic force, producing different atomic structures, different chemistry, different stellar physics. It might have a different electron mass, altering the stability of atoms and the possibility of molecules. It might have a different cosmological constant, producing a universe that either collapsed immediately under its own gravity or expanded so rapidly that matter never had the opportunity to clump into galaxies and stars. It might have different numbers of large spatial dimensions, making its geometry and its physics categorically unlike ours in ways we cannot fully describe from inside our own pocket. Most of these configurations would be sterile. Most of the 10 to the 500 vacuum states in the string theory landscape correspond to universes in which the physical constants land in regions incompatible with the existence of anything complex. Universes that are too hot or too cold, too dense or too sparse, too short-lived or too rapidly dispersed. Universes where atoms are unstable, where stars cannot form, where nuclear reactions cannot produce the heavier elements that carbon-based chemistry requires. The overwhelming majority of pocket universes in this picture are empty of complexity, but in an infinite number of pockets, even an extraordinarily small fraction represents an infinite number of universes, including inevitably pockets whose physical constants fall in the narrow range compatible with complexity, with stars and planets and chemistry and observers. This is the string theory landscape in its cosmological context, not merely a catalogue of mathematical possibilities, but in the eternal inflation framework, a catalogue of actual places, actual universes, each permanent, each inaccessible from every other, separated not by distance, but by the inflating background that will always lie between them and by the fundamental difference in their physics. Whether any of this is testable is the sharpest question in contemporary theoretical physics, and the honest answer is that direct confirmation is almost certainly beyond any experiment we can conceive of. You cannot send a probe to another pocket universe. You cannot detect their light or their gravitational waves because the inflating background between them and us is expanding faster than any signal can cross. They are not merely very far away. They are causally disconnected in a way that makes our horizon with the merely spatial, unobservable universe look trivially approachable by comparison. But indirect evidence is not entirely impossible, and one candidate has attracted genuine scientific attention rather than mere speculation. In eternal inflation, pocket universes are not static. As each bubble of ended inflation nucleates within the inflating background and expands, it can, in certain geometric configurations, collide with adjacent bubbles. Two pocket universes growing toward each other through the inflationary background can intersect, and when they do, the collision deposits energy asymmetrically into the CMB of each, leaving a specific circular imprint on the temperature pattern of the sky. A disk of anomalous temperature with a distinctive profile at its edge, appearing against the otherwise statistically uniform background. The CMB cold spot has been examined as a candidate for exactly this signature. The region roughly centered on the constellation Eridanus, approximately 5 degrees across, and anomalously cold by an amount that exceeds standard inflationary predictions for a region of that size, has a profile broadly consistent with what a bubble collision would produce. The probability of the cold spot arising by chance in a purely standard inflationary universe is estimated at somewhere between 1 and 2%, low enough to attract attention, not low enough to compel a conclusion. The leading alternative explanation is a supervoid, a large region of below-average matter density at a redshift of approximately 0.2, through which CMB photons traveling toward us have lost energy via the integrated Sachs-Wolf effect. When photons travel through a void, they must climb out of a shallow gravitational potential well. As the universe expands and dark energy stretches the void, the well flattens during the photon's transit, and the photon exits slightly less energetic than it entered, slightly colder. Galaxy surveys have found evidence for an underdense region in the direction of the cold spot, and this has shifted the consensus toward the supervoid as the primary explanation. But the supervoid does not fully account for the temperature deficit. The cold spot is measurably colder than the supervoid alone predicts. The gap is not enormous, not screaming for an exotic explanation, but it has not closed with better data. It remains slightly open, and in that opening, a small but rigorous community of physicists continues to ask whether something else is contributing, something on the other side of the boundary between what we can see and what we cannot. The bubble collision hypothesis has not been confirmed. It has not been ruled out. It sits in the status that physics reserves for ideas that are consistent with the data, motivated by a serious theoretical framework and resistant to definitive test by current instruments. Waiting. The multiverse of eternal inflation is at its core not a comfortable idea. It is not comfortable for physicists who believe that any genuine scientific theory must make predictions that can, in principle, be tested. If the other pockets are permanently inaccessible, if no signal from them can ever reach us, if their existence or non-existence makes no detectable difference to any observation we can perform, then what kind of claim is it that they exist? Is it a scientific hypothesis, or is it a mathematical extrapolation that happens to be consistent with the equations? but sits outside the domain of empirical science. This debate is real. It is conducted between serious people with serious arguments on both sides, and it has not been resolved. Some physicists, among them David Gross and Paul Steinhardt, have argued strenuously that a theory producing an infinite number of universes with every possible set of physical constants is not a predictive framework at all, that it explains nothing because it is consistent with everything, that the landscape of string theory combined with the further Fortinal inflation is not a solution to the fine-tuning problems of physics but an abdication of the demand for explanation, replacing a precise answer with an infinite shrug. Others, among them Linda and Susskind and Weinberg, counter that the multiverse is no different in principle from other unobservable extensions of physics, that the interior of black holes is also causally disconnected from external observers, and that the criterion of testability has never required direct observation of every entity a theory posits, that what matters is whether the theory makes predictions that can be tested within our observable sphere, and eternal inflation does make such predictions. The spectral index of the CMB fluctuations, the absence of magnetic monopoles, the specific statistical properties of the density perturbations, all of these are confirmed. The multiverse is not separately confirmed, but it is the environment within which the confirmed predictions arise. What is not in dispute is this: the mathematics that produces the spectral index measurement of 0.9649, the measurement that confirms slow-roll inflation to extraordinary precision, is the same mathematics that followed without modification, implies eternal inflation. You cannot accept the first result and cleanly reject the second. They come from the same equations. If you trust the equations enough to cite the spectral index as evidence for inflation, you are trusting the same equations that say inflation is eternal. The multiverse is not an add-on, it is a consequence. And if it is real, then the observable universe, all of it, the 2 trillion galaxies, and the 46.5 billion light-year radius, and the 13.8 billion years of history, and every photon that has ever arrived at any instrument we have built is one pocket, one local ending of inflation, one bubble in a foam of bubbles that has been forming and growing and will continue forming and growing forever. Our entire cosmic history, from the moment of reheating to the last star going cold in the far future, is a local episode within a structure so vast that comparing it to what we can see is like comparing a single atom to the observable universe. We are not at the center, we are not at the edge, we are in a bubble, and the bubble is one of infinitely many. Whether that is true, whether the equations are describing something real or generating a mathematical structure that has no physical counterpart, is a question that sits precisely at the boundary between what physics can currently determine and what it may never be able to determine. And sitting with that uncertainty, holding it without resolving it artificially in either direction, is perhaps the most honest intellectual position available to anyone thinking carefully about this subject. The observable universe is not the universe. It is a pocket, and the pocket has walls, and beyond the walls, if the mathematics is to be trusted, the process that built the walls is still running. It will never stop. In 1998, 2 teams of astronomers were competing to measure the same thing, not racing in the dramatic sense, not enemies, but working in parallel independently, each checking the other's methodology through the simple fact of their separate existence. Both teams were using a specific type of exploding star to map the expansion history of the universe, and both teams expected to find the same result that almost every cosmologist at the time would have predicted, the same result that the straightforward application of gravitational physics seemed to demand. They expected to find that the expansion of the universe was slowing down. This was not an unreasonable expectation. It was by every available physical argument the obvious prediction. The universe contains matter. Matter has mass. Mass produces gravity. Gravity is attractive. Everything in the universe is pulling on everything else, and that mutual attraction acting over the entire history of cosmic expansion should be doing what gravity always does, decelerating the motion of objects moving apart from each other. The Big Bang had set everything flying outward. Gravity was putting on the brakes. The question the 2 teams were trying to answer was precisely how hard those brakes were being applied. How much was the expansion slowing, and would it slow enough to eventually reverse, pulling everything back together in a final collapse, or would it slow but never quite stop, allowing the universe to expand forever at an ever-decreasing rate? Those were the options anyone was thinking about. Deceleration possibly followed by collapse, or deceleration continuing indefinitely toward a cold and empty future. The question was one of degree, not of direction. The type of exploding star both teams were using is called a Type Ia supernova, and it is one of the most useful objects in observational astronomy for reasons that come down to a remarkable regularity in its behavior. A Type Ia supernova occurs in a binary star system, two stars orbiting each other, where one of the stars is a white dwarf, the dense remnant of a star that has exhausted its nuclear fuel. When the white dwarf accretes enough material from its companion to exceed a specific mass threshold known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, the electron degeneracy pressure that was holding it up against gravity can no longer support its weight. The white dwarf collapses and then explodes in a thermonuclear detonation of extraordinary violence, briefly outshining its entire host galaxy. What makes this explosion useful is its consistency. Because the explosion is triggered at the same mass threshold every time, the physics of the detonation is remarkably similar from one event to the next. The intrinsic brightness of Type Ia supernovae, their absolute luminosity at peak, is approximately the same regardless of where in the universe they occur, with corrections that astronomers have learned to apply based on the shape of light curve, how quickly the brightness rises and falls. This makes them what cosmologists call standard candles, objects of known intrinsic brightness that can be used to measure distances. If you know how bright something actually is and you measure how bright it appears, the difference tells you how far away it is, the same way you can estimate the distance to a streetlight if you know its wattage and measure the illumination it provides. By measuring the apparent brightness of Type Ia supernovae at known redshifts, comparing how bright they appear to how bright they should be at those distances in a universe undergoing various rates of deceleration, both teams were trying to pin down the deceleration parameter precisely. The Supernova Cosmology Project had each assembled samples of distant supernovae and were working through the analysis independently. What they found was not deceleration. The distant supernovae were fainter than expected. Not dramatically fainter, not obviously fainter to the naked eye, but statistically, systematically, measurably fainter than any decelerating universe model predicted. Fainter means farther. Farther at those distances and redshifts means the universe was expanding more slowly in the past than it is today. Not slowing down, speeding up. The expansion of the universe was not decelerating, it was accelerating. Both teams were sufficiently alarmed by their own result that they spent considerable time searching for errors before they trusted it. Perlmutter's group and Schmidt's group each went through their data independently, looking for systematic biases, calibration errors, unusual dust properties in distant galaxies, anything that could make distant supernovae appear fainter than they truly are without implying acceleration. They found nothing sufficient to explain the discrepancy. The result held. Both teams published in 1998, and the two independent analyses agreed with each other. Something was pushing the expansion of the universe to go faster and faster, overcoming the decelerating pull of gravity at the largest scales, and had been doing so for approximately the last 5 billion years. The discovery won the Nobel Prize in Physics in 2011, awarded jointly to Perlmutter, Schmidt, and Rees. It remains, in the assessment of many physicists, the most genuinely shocking observational result in the history of modern cosmology. Not shocking in the sense of being unexpected from a particular theoretical framework, but shocking in the deeper sense of revealing that something fundamental about the universe had been entirely absent from everyone's picture of it. Something real, something dominant, something accounting for the majority of the universe's total energy content had gone completely unnoticed until two groups of astronomers tried to measure how fast the cosmos was putting on the brakes. Whatever is causing the acceleration has been named dark energy. The name is honest about what it conceals. Dark energy is not dark matter. Dark matter is a form of matter that does not interact with electromagnetic radiation, does not emit or absorb light, but does interact gravitationally, clustering around galaxies and influencing the rotation of stellar orbits. Dark matter's existence is inferred from gravitational effects and is supported by multiple independent lines of evidence. It is a form of matter strange and unknown in its composition, but matter in the sense of being a substance with mass that clusters and gravitates. Dark energy is different in kind. It is a form of energy that permeates all of space uniformly. It does not cluster. It does not dilute as space expands. Unlike matter or radiation, which spread out and become less dense as the volume they occupy, increases dark energy maintains a constant energy density regardless of how much space grows, and it exerts what the equations of general relativity describe as a negative pressure, a repulsive effect on the geometry of spacetime that drives acceleration rather than deceleration. It currently accounts for approximately 68% of the total energy content of the universe. Dark matter accounts for roughly 27%. Ordinary matter, everything made of protons and neutrons and electrons, every atom in every star and planet, and human body accounts for approximately 5%. The universe we can touch and see and measure directly is a 5% minority in a cosmos, dominated by two things we do not understand. The simplest model for dark energy is Einstein's cosmological constant, the term he introduced into his equations of general relativity in 1917 and later called his greatest blunder. In the cosmological constant model, dark energy is the energy of empty space itself, the vacuum energy of quantum fields, a baseline hum of energy that exists even when all matter and radiation have been removed from a region when the temperature has dropped to absolute zero and nothing is left. It is characterized by an equation of state parameter, designated as W, defined as the ratio of pressure to energy density equal to -1, meaning its pressure is exactly equal and opposite to its energy density, the specific relationship that produces the observed acceleration. The cosmological constant model fits the current data reasonably well, but it carries with it a problem so severe that it has been called, with only slight exaggeration, the worst prediction in the history of science. Quantum field theory, the framework that describes all known particles and forces with extraordinary precision, predicts a vacuum energy density associated with the zero-point fluctuations of all quantum fields. Every quantum field, even in its ground state, has energy. The uncertainty principle guarantees it, and when you sum up the contributions from all known quantum fields, the predicted vacuum energy density comes out to a value approximately 120 orders of magnitude larger than the observed dark energy density, one followed by 120 zeros times too large. To put that discrepancy into some kind of perspective, though, perspective barely applies at this scale. If you wanted to represent the predicted vacuum energy as the distance from here to the edge of the observable universe, the observed dark energy would be represented by a distance smaller than the diameter of a single proton. That is how wrong the prediction is. That is how far the most successful physical theory in history misses when it tries to calculate the energy of empty space. Either quantum field theory is profoundly wrong about vacuum energy in some way we have not yet identified, or there is some mechanism that cancels the predicted vacuum energy almost, but not quite completely, leaving just the tiny residual we observe as dark energy, something that reduces a number of order 10 to the 120 down to a number of order 1 with a precision of 120 decimal places for no reason that any current physics can explain. This is the cosmological constant problem. It sits at the center of theoretical physics as perhaps the deepest unsolved puzzle in the field. It connects quantum mechanics to general relativity at the most fundamental level and finds a discrepancy so enormous that bridging it would require a revolution in our understanding of both. No one knows what that revolution would look like. No one has a compelling proposal for the cancellation mechanism. The problem has been known since the 1960s, and it has not been solved. This is part of why the results from the dark energy spectroscopic instrument known as DESI have attracted intense attention from the cosmological community. DESI is conducting the largest three-dimensional map of the universe ever attempted, measuring the positions and redshifts of tens of millions of galaxies across a vast range of cosmic history. It uses the imprint of baryon acoustic oscillations, the same frozen sound waves from the early universe we encountered in the CMB, but detected this time in the three-dimensional distribution of galaxies rather than in the two-dimensional temperature pattern of the microwave background. By measuring how the characteristic scale of those oscillations has changed over cosmic time, DESI is tracing the expansion history of the universe with unprecedented precision, and from that expansion history, it is measuring dark energy's equation of state parameter W and asking whether it has remained constant over cosmic history or whether it has evolved. The first year of DESI data released in 2024 produced a result that stopped people in the field. The data showed a hint, not a confirmed detection at the 5 sigma threshold required for a claimed discovery, but a statistically significant hint that W is not exactly -1, that it may be evolving with time, taking a different value at different epochs of cosmic history. A value of W that changes over cosmic history would rule out the simplest cosmological constant model. The cosmological constant by definition cannot evolve. It is a constant. If W is changing, dark energy is not the energy of empty space. It is something more dynamic, something with its own field, its own evolution, its own history. The hint from DESI is consistent across multiple independent analysis approaches within the data set, which makes it harder to attribute to a statistical fluctuation or a single systematic error. The cosmological community is watching the subsequent releases of DESI data with the kind of attention that precedes either a revolution or a disappointment, and it is not yet clear which it will be. The leading class of dynamical dark energy models is called quintessence. In these models, dark energy is a scalar field, not unlike the inflaton field that drove inflation in the earliest moments of the universe, that is slowly rolling down its potential energy landscape, driving accelerated expansion as it does so. The structural parallel between inflation and quintessence is something theorists have noted with interest. Both invoke a slowly rolling scalar field. Both produce epochs of accelerated expansion. Both leave observable signatures in the large-scale structure of the cosmos. One operates at the very beginning, driven by a field at enormous energies, producing the near-exponential expansion that smoothed and seeded the universe. The other operates now driven by a field at extraordinarily low energies, producing the gentle, accelerated expansion we currently observe. Whether this parallel is superficial, or whether it reflects some deeper unity, whether a single field can account for both epochs in what theorists call quintessential inflation, is unknown. What is not unknown is the direction in which dark energy is pushing the future of the observable universe, and that direction, followed carefully, is one of progressive isolation and eventual silence. The cosmic event horizon, the boundary beyond which no signal sent today can ever reach its destination, currently sits at approximately 16.6 billion light-years. Galaxies just inside that boundary are at this moment barely within the range of causal contact. Any signal we send today will just barely reach them over billions of years of travel as they continue to recede. But dark energy is causing the expansion to accelerate. The recession velocity of distant galaxies is increasing. Galaxies that are today marginally inside the event horizon will over the coming billions of years be carried across it by the accelerating expansion. They will recede into the region from which no signal of ours can ever follow, and they will go dark. Not suddenly, not in any way that would register on any human time scale, but inexorably the set of galaxies that are in causal contact with us is shrinking. Not because the observable sphere defined by past light travel is getting smaller, that sphere continues to grow slowly as more ancient light arrives, but because the set of galaxies we could in principle ever again interact with, ever communicate with, ever receive a future signal from is contracting as dark energy drives the event horizon inward in co-moving terms. Project this forward across cosmic time and the picture that emerges is stark. In roughly 2 billion years, the Andromeda Galaxy, currently about 2.5 million light-years away and approaching us under the mutual gravitational attraction of the local group, will merge with the Milky Way. The two galaxies will collide their stars, passing through each other in a process lasting hundreds of millions of years, their central black holes eventually merging, producing a new elliptical galaxy that astronomers have provisionally named Milkomeda. This merger is not a consequence of dark energy. It is a consequence of the gravitational binding of the local group, the few dozen galaxies that are close enough to each other that their mutual gravity exceeds the expansive push of dark energy at local scales. Gravity wins locally. Dark energy wins at large scales. The boundary between the two regimes falls at distances of a few million light-years, roughly the scale of the local group. Everything gravitationally bound within the local group will stay bound. Everything outside the local group is already being carried away by the expansion already receding at rates that will only increase. In roughly 100 billion years, approximately 7 times the current age of the universe, the acceleration of the expansion will have carried every galaxy outside the local group, beyond the cosmic event horizon. The sky, for any observer who might exist at that epoch, will contain no external galaxies, not because those galaxies have been destroyed or because space has ended, because the light from them will have been redshifted by the expansion to wavelengths so long that no instrument of any kind could detect it. They will have faded below any possible threshold of observation, their photons stretched by 13 billion years of additional expansion into wavelengths longer than the diameter of the observable universe itself. Invisible, gone for all practical and theoretical purposes of observation. The evidence of the large-scale structure of the cosmos, the web of galaxy filaments and clusters and voids that the CMB fluctuations seeded and 13.8 billion years of gravitational collapse built, will have vanished from the observable sky. An observer at that epoch, however sophisticated, however capable their instruments, would have no observational evidence that the universe ever contained anything beyond their local gravitational cluster. They would look out at a sky of extraordinary darkness and have no way of knowing from that sky alone that 2 trillion galaxies once populated the observable universe, or that the large-scale structure of the cosmos told a story of inflation and acoustic oscillations and dark matter and the geometry of spacetime. The universe will have hidden its own history, not metaphorically, literally. The evidence will be gone, carried beyond the event horizon by the same dark energy that is today pushing the expansion toward that future erasure. And in the most extreme scenario, the future does not stop at a dark and isolated sky. It continues into territory more violent and more total. If dark energy is not constant, but grows stronger over time, a class of models called phantom dark energy, characterized by an equation of state parameter W less than -1, then the acceleration does not merely continue at a steady rate, it intensifies. And if it intensifies without limit, the consequences proceed in a specific and devastating sequence. First, the acceleration overcomes the gravitational binding of galaxy clusters, tearing apart the structures that survive the expansion of the background. Then it overcomes the gravitational binding of individual galaxies, then the binding of individual star systems, then the molecular bonds holding planets and rocks together, then the atomic bonds holding molecules together, then the electromagnetic forces binding electrons to nuclei. And finally, in the ultimate expression of this process, it overcomes the strong nuclear force binding quarks inside protons and neutrons. Everything tears apart. Not through heat, not through collision, not through any conventional violent process. Through the expansion of space between the components of matter, the universe ends not in a bang, not in a cold, slow fade, but in a dissolution so complete and so uniform that the last things to go are the fundamental particles themselves, shredded one by the geometry of spacetime. This is called the Big Rip, and whether it is the fate of this universe depends entirely on whether dark energy is truly phantom, on whether W is less than -1, and whether it is decreasing, which the current data does not require, but does not exclude. Even without the Big Rip, even in the gentler scenario where dark energy maintains its current value and the expansion accelerates steadily but not catastrophically, the trend is unambiguous. The observable universe is becoming more isolated. The fraction of the cosmos accessible to any observer is shrinking. The evidence of the universe's history is being systematically erased by the same force that is currently under investigation by the most sophisticated astronomical survey ever attempted. Inflation built the initial boundary. It pushed the overwhelming majority of reality beyond the causal horizon in the first fraction of the first second of existence, and it did so as an unavoidable consequence of the mechanism that made our universe flat and smooth and seeded with structure. Dark energy is continuing that work. It is reinforcing the boundary, tightening it, carrying more and more of the cosmos beyond the event horizon with every passing billion years. The progressive hiddenness of reality is not a static feature of this universe. It is a dynamic process, ongoing, directional, and accelerating. We exist at a cosmologically fortunate moment. The sky above us contains 2 trillion galaxies. The CMB is still detectable, still legible, still carrying the imprint of inflation in its temperature fluctuations and its spectral index and its acoustic peak structure. The large-scale structure of the cosmos, the filaments and voids and clusters built by 13.8 billion years of gravitational evolution from inflationary seeds, is still visible in galaxy surveys. The evidence is all there, accessible, readable, speaking clearly about the universe's origin and geometry and content. It will not always be. Every eon that passes is an eon in which more of the evidence is carried beyond the event horizon, more of the structure is diluted, more of the sky goes dark. The observers who come after us, if any come after us across the vast timescales of the universe's future, will inherit a smaller window, a quieter sky, a universe that has done an even more thorough job of concealing itself. We are seeing more of it right now than any observer ever will again. The window is open, it is still open, but dark energy is slowly, patiently, relentlessly closing it. And the question worth holding as we move toward the final chapter of this journey is what it means that we know this, that we can calculate the rate at which the window closes, map the trajectory of the event horizon, trace the history of dark energy's influence backward through supernova observations and forward through the equations of general relativity. That the same universe which is hiding itself from us has given us inside our small and shrinking bubble the physics required to understand exactly how and why it is hiding. That is not nothing. It is in some ways the most extraordinary thing about the situation. There is a question that sounds on first hearing like philosophy dressed up as physics. It sounds like the kind of question that gets asked at the end of a long night when the conversation has moved past what the data directly supports and into the territory where speculation and mathematics blur together. The question is, this is the boundary of the observable universe, merely a limit on what we can see, or is it something more fundamental than that? Is the horizon simply the edge of our information, a practical constraint imposed by the finite age of the universe and the finite speed of light? Or is it a physical surface with genuine thermodynamic reality, a boundary that has temperature and entropy and information content in the same precise sense that a black hole's event horizon has those properties? The answer that emerges from the most rigorous theoretical work done over the last 3 decades is the second one, and understanding why requires a brief journey into one of the deepest and strangest ideas in contemporary physics. In the early 1970s, a young graduate student named Jacob Bekenstein was working on a problem that his supervisor, the physicist John Wheeler, considered almost paradoxical in its simplicity. The problem was this. The second law of thermodynamics states that the total entropy of a closed system never decreases. Entropy, in the technical sense, is a measure of the number of microscopic configurations available to a system, a measure of disorder, of the information required to fully specify the state of every component. The second law says that in any physical process, the total entropy of the universe either stays the same or increases. It never spontaneously decreases. But what happens when you throw something into a black hole? A black hole is a region of spacetime from which nothing, not matter, not radiation, not any signal of any kind can escape. When you drop an object into a black hole, all the information about that object, its composition, its temperature, its entropy, appears to vanish from the observable universe. The black hole absorbs it and gives nothing back. If the entropy of the absorbed object is simply lost, the total entropy of the universe outside the black hole decreases. The second law is violated. Bekenstein proposed a resolution: black holes must themselves carry entropy. The entropy that falls into a black hole is not lost. It is transferred to the black hole, which grows in entropy by at least the amount that was absorbed. And Bekenstein calculated what that entropy must be. The result was striking. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon, the surface area of the boundary beyond which nothing can escape, not the three-dimensional space inside, the two-dimensional surface surrounding it. Stephen Hawking initially resisted this idea, arguing that if black holes have entropy, they must also have temperature, and if they have temperature, they must radiate, which seemed impossible given that nothing can escape from inside a black hole. But Hawking then performed one of the most celebrated calculations in theoretical physics, applying quantum mechanics to the curved spacetime near a black hole's event horizon, and found that black holes do indeed radiate. They emit thermal radiation at a temperature inversely proportional to their mass, now called Hawking radiation, and they carry entropy proportional to the area of their horizon, exactly as Bekenstein had proposed. The Bekenstein-Hawking formula for black hole entropy is engraved in the foundations of modern theoretical physics. Its implications extend far beyond black holes. It says something profound about the relationship between information area and the geometry of space-time. The information content of any region of space is not proportional to its volume. It is proportional to the area of the surface bounding that region. Doubling the linear size of a region increases its volume by a factor of 8, but only increases its information content by a factor of 4. This is the holographic principle. It was developed in its full generality by Gerard Hooft and Leonard Susskind in the 1990s, working from the Bekenstein-Hawking result and pushing it toward its most general implications. The name comes from the analogy with a hologram, a two-dimensional surface on which a three-dimensional image is encoded. The holographic principle says that the universe works like a hologram, the three-dimensional world we inhabit, with all its matter and fields and forces and history, is in some profound sense encoded on a two-dimensional surface. Volume and information do not scale together the way intuition suggests. The surface contains the interior. Juan Maldaceno's work in 1997 now, one of the most cited papers in the history of physics, gave this principle its most mathematically rigorous formulation. Maldaceno showed that a specific theory of quantum gravity in a particular type of curved spacetime is exactly equivalent to a quantum field theory living on the boundary of that spacetime, not approximately equivalent, not analogous, exactly equivalent, the same physical reality described by two completely different mathematical languages, one operating in the volume and one operating on the surface. The duality is precise and total. This is called the ADS, CFT correspondence, and while its direct application to our universe is not straightforward, because our universe is not the specific curved spacetime, Maldaceno's calculation applies to its implications for how we think about horizons and information have been transformative. It established beyond any serious theoretical doubt that the holographic principle is not a metaphor. It is a structural feature of how quantum gravity works. Now apply this to our cosmological horizon. Our universe is not the anti-de Sitter space of Maldaceno's calculation. It is as dark energy increasingly dominates, approaching what physicists call de Sitter space, a universe governed by a positive cosmological constant, expanding exponentially with a cosmological event horizon surrounding every observer. The thermodynamic properties of this horizon have been worked out carefully, beginning with work by Gibbons and Hawking in 1977. And what they found is that the cosmological event horizon, the boundary at approximately 16.6 billion light-years beyond which no signal we send today will ever reach, has a temperature. It has an entropy. It has an information content. And that information content is proportional to the area of the horizon, just as in the black hole case. The de Sitter entropy, the total information content of everything within our cosmological horizon, is a specific finite number. It is proportional to the area of the event horizon measured in units of the Planck area, the fundamental quantum of area set by the constants of nature. The number is enormous by ordinary standards, roughly 10 to the 122 bits, but it is finite, and crucially, it is a property of the boundary, not the volume. The horizon encodes the interior. The two-dimensional surface at 16.6 billion light-years contains all the information about everything within it. What this means taken seriously is that the cosmological horizon is not merely a limit on our information. It is a physical surface with genuine thermodynamic significance. It has a temperature measurable in principle, though, so small as to be far beyond any practical detection. It has an entropy, a precise count of the distinguishable states available to the system it bounds. It has an information capacity, a finite maximum amount of information that can exist within the volume it encloses. The boundary between the observable and the unobservable is not an arbitrary line drawn by the accident of our location in spacetime. It is a surface with physical reality in the deepest sense that theoretical physics can give to anything. The horizon is real. Not real in the way that a rock is real, something you can touch and weigh and photograph. Real in the way that the laws of thermodynamics are real, in the way that the speed of light is real, in the way that the quantum of angular momentum is real. Real as a structural feature of how physics operates. And what lies beyond it? The answer has layers, and the layers differ in how certain they are, ranging from what follows necessarily from the data we have, through what follows from well-supported but not confirmed theory, to what follows from frameworks that are mathematically serious but empirically unresolved. Each layer deserves to be held with the appropriate degree of confidence, neither dismissed as speculation nor elevated beyond what the evidence warrants. The first layer is the most certain, and it requires no new physics, no unconfirmed theory, no speculation beyond the standard cosmological model taken at face value. Beyond our horizon is more space structured by the same physics that structures the space inside our horizon, seeded by the same inflationary perturbations, governed by the same laws of gravity and electromagnetism and nuclear physics, populated by galaxies and stars and whatever other structures those conditions produce across 13.8 billion years of gravitational evolution. The Vardanyan, Trotter, and Silk analysis tells us the minimum at least 251 times the radius of our observable sphere, implying at least 15.8 million observable universes worth of content, 32 sextillion galaxies minimum beyond our horizon, all dark to us, all governed by the same physics, all formed from the same initial conditions stretched to cosmic scales by the same inflationary epoch. This is not speculation. It does not require any physics beyond what the Planck satellite measured. It is the minimum that follows from taking the flatness measurement seriously and applying the mathematics of inflation to it with no additional assumptions. If you trust the data, this is what is there. Invisible, inaccessible, real. The second layer is topology. The possibility that space, rather than extending without limit in every direction, folds back on itself in a multiply-connected geometry, a hypertorus, or some more exotic topological structure in which traveling far enough in any direction brings you back to where you started. The universe finite in total volume with no edge and no center, locally flat in every neighborhood, but globally wrapped in a way that makes the full extent of space finite. In this scenario, what lies beyond our horizon in any given direction is eventually the same space we occupy approached from the other side of the loop after a journey of unimaginable length. The universe is a hall of mirrors so vast that the reflection has never had time to complete its journey back to us. This cannot be confirmed with current data because inflation has pushed any topological identification scale well beyond our observational reach. But it cannot be ruled out. It is consistent with everything we observe. It is mathematically well-defined and physically motivated. It sits in the category of things we genuinely do not know and may never know from inside our causal bubble. The third layer is the full inflationary volume, the complete extent of what the inflationary epoch created, which vastly exceeds the minimum implied by the Vardanyan analysis. The duration of inflation and the energy scale at which it occurred are not precisely known from current observations. The minimum expansion factor of 10 to the 26th is a lower bound derived from the most conservative models. Many well-motivated inflationary models predict expansion factors orders of magnitude larger. Under those models, the ratio of the actual universe to our observable sphere is not 15.8 million to 1. It is a number without any meaningful analogy in human experience. The regions that were causally connected to ours before inflation, that shared the same pre-inflationary equilibrium, that experienced the same initial conditions, and the same smoothing and seeding by the inflationary epoch, were pushed beyond our horizon during inflation and have been receding ever since. They share our physical laws, they share our type of physics, they were part of the same pre-inflationary patch, and their subsequent 13.8 billion years of history are permanently inaccessible to us running in parallel, with ours separated by a boundary that no physical process operating within this universe can ever bridge. The fourth layer is the multiverse of eternal inflation, the foam of pocket universes produced by the self-reproducing nature of inflation under quantum fluctuations, each one a local ending of inflation, each one potentially settled into a different vacuum state, each one potentially governed by different physical constants and different versions of the fundamental forces. This is the most speculative layer and the one that sits most uncomfortably at the boundary between physics and philosophy. It follows from the quantum mechanics that inflation requires. It is not arbitrary, but its direct confirmation may be permanently beyond reach. What ties all four layers together, what makes them not four separate speculations but four chapters of a single story, is that every one of them is a consequence of the same physics. The flatness requiring such extreme precision, the inflation resolving that precision by exponentially stretching space, the causal horizon that the stretching built into space-time, the dark energy reinforcing that horizon and continuing its work indefinitely. These are not separate facts assembled from different sources. They are one story told by one set of equations applied consistently to one universe from its first moment to its last. And that story read in its entirety says something specific and strange about the relationship between our existence and our ignorance. The same process that made this universe flat, that smoothed out its geometry and equilibrated its temperature and diluted its monopoles and seeded its structure with quantum fluctuations stretched to cosmic scales, is the process that placed the overwhelming majority of reality permanently beyond the reach of any observation any observer inside this universe can ever make. The solution and the concealment are not separate events in sequence. They are the same event viewed from two different angles. The mechanism that built us built the wall, not metaphorically, causally. The physics that produced conditions compatible with the existence of observers is identically the physics that guaranteed those observers would never see most of what exists. Our existence and our ignorance share a common origin. There is a question in the philosophy of science about what it means for something to be permanently unknowable. Not unknown because the instruments are not yet sensitive enough. Not unknown because the theory is incomplete, but unknowable in principle, because the answer is structurally outside the reach of any possible observation from any possible location within the system. It used to feel like an academic question, the kind of puzzle philosophers entertained in the absence of real problems. It no longer feels that way. The questions we have been tracing throughout this entire journey are in that category. Not metaphorically, literally. We cannot build a telescope that sees beyond the particle horizon because the light from beyond it has not reached us, and in most cases never will. We cannot send a probe across the distance that inflation opened. We cannot observe the total size of the universe, the topology of space beyond our observable sphere, the structure of other inflationary bubbles, or the physical constants of other pocket universes. These are not questions waiting for a better instrument or a future theory. They are questions that the physics of this universe has placed permanently and irrevocably outside the domain of empirical access. And yet, the physics that governs what lies beyond our horizon also governs what happens inside it, and it leaves traces. The flatness we measure implies the extension we cannot see. The spectral index of the CMB perturbation 0.9649 confirms the inflationary origin of structure to a precision that rules out all simpler alternatives. The acoustic peaks in the CMB power spectrum sit exactly where flat geometry models predicted, independently confirming the geometry measurement through a completely different observable. The baryon acoustic oscillation signal in the distribution of hundreds of millions of galaxies agrees with the CMB flatness measurement, a cross-check from an entirely independent dataset. The primordial gravitational wave background, if detected by the next generation of CMB experiments, would measure the energy scale of inflation directly. That measurement would constrain the range of inflationary models, and with it, the probable size of the inflated volume. The matched circles in the CMB that would reveal topology if they exist within our observable sphere. The bubble collision signatures that would confirm eternal inflation if found. The dynamics of dark energy being measured by DESI and its successors, which will constrain the nature of the field driving acceleration and its trajectory into the future. The gravitational wave backgrounds detectable by next-generation observatories, which may carry information from epochs earlier than the CMB, perhaps from the inflationary epoch itself. We can infer what we cannot observe. The inference is incomplete. It will always be incomplete, but it is not nothing. It is in some ways the most profound achievement of physics as a discipline that local equations applied carefully to local observations have consequences that extend far beyond what any experiment can directly confirm, and that those consequences can be tested through the imprints they leave in the local data. The universe is not fully cooperating with our desire to see beyond the horizon, but it has left its physics intact all the way to the edge, and those physics read carefully tell us more about what lies beyond than we have any right to know. The observable universe, 46.5 billion light-years in radius, 2 trillion galaxies, a surface of last scattering encoded in the CMB at a temperature of 2.725 Kelvin, is a window. It is a small window. It is a biased window because we are embedded inside it and cannot step outside to check the view from a neutral position. It is a bounded window because the physics that made it habitable also made it finite in causal reach. And it is a shrinking window as dark energy continues its patient work of carrying more and more of the cosmos beyond the boundary that inflation established. But it is still a window, and what it looks out on, what the equations say is on the other side of the glass, is not emptiness. It is not silence. It is not a void waiting to be filled by a more powerful telescope. It is more universe, incomparably more universe. Universe that formed by the same physics, under the same laws, from the same initial conditions. Universe that has its own 13.8 billion years of history, its own structures, built by gravity from inflationary seeds, its own stars burning through their nuclear fuel, its own darkness between those stars. Universe that we will never read. Universe that may, in the eternal inflation picture, vary in its physical constants and its fundamental character from pocket to pocket, across a landscape of possibilities so vast that our entire observable cosmos is a single point within it. Universe that is right now at this moment existing in complete indifference to the fact that we cannot see it. The wall is not the end of the story. It is the edge of the chapter we are in. You started this journey looking at a lie, not a malicious one, not one constructed by anyone with an agenda. A lie built into the most natural act of human perception, the act of looking up at a clear night sky and feeling in that quiet and wordless way that you are seeing the whole of things. That the darkness above you, filled with light from 100 billion stars in your own galaxy alone, represents the full account of what exists. It does not. What you have been shown across the length of this journey is not simply that the universe is larger than it looks. That would be unremarkable. Everything in astronomy is larger than it looks. What you have been shown is something more specific and more strange. That the universe is hidden from us, not by accident, not by the inadequacy of our instruments, not by a temporary limitation waiting for the next generation of telescopes to resolve, but by structure, by physics, by the same equations that made it possible for anything to exist at all. Let's hold the numbers one more time because they deserve to be held. The observable universe has a radius of 46.5 billion light-years. Within that sphere, there are approximately 2 trillion galaxies. The cosmic microwave background, the oldest light we can detect, was released when the universe was 380,000 years old and has been traveling toward us ever since arriving now at a temperature of 2.725 Kelvin, barely above the coldest anything can ever be. The flatness of space, measured by the Planck satellite across that entire sphere, is 1 to within 0.5%. The spectral index of the primordial density fluctuations is 0.9649, in extraordinary agreement with the predictions of slow-roll inflation. The universe is 68% dark energy, 27% dark matter, and 5% everything we have ever directly touched or seen or measured. These are not estimates. These are the most precisely determined facts about the largest scales of physical reality that any civilization we know of has ever established. They represent centuries of accumulated observation, 3 generations of dedicated CMB satellites, surveys of hundreds of millions of galaxies, and the application of mathematical frameworks developed over more than 100 years. Theoretical physics. They are within their stated uncertainties true, and what they imply, followed carefully and without flinching, is that the observable universe is a minimum of 251 times smaller in radius than the actual universe. That at least 15.8 million observable spheres worth of content exists beyond our horizon, invisible and inaccessible. That 32 sextillion galaxies at minimum lie beyond any boundary we will ever cross. That the inflationary epoch which produced these numbers lasted less than 10 to the negative 32 seconds and expanded space by a factor of at least 10 to the 26th. That the same process is almost certainly still running, producing new pocket universes in a self-reproducing background that extends beyond every boundary we have discussed. That dark energy is currently tightening the event horizon, carrying more galaxies beyond causal reach with every passing billion years, and will eventually leave any future observer with a sky containing nothing beyond their local gravitational cluster, no evidence in the sky that the larger universe ever existed. This is what we know. This is what the data says when you follow it without stopping at the comfortable parts. But there is something beneath the numbers that deserves more than a moment. Throughout this journey there has been a pattern worth naming explicitly, because once you see it, it changes how you understand not just cosmology, but the nature of knowledge itself. Every time we found a mechanism that made the universe livable, we found that the same mechanism made the universe mostly invisible. The inflation that solved the flatness problem hid the overwhelming majority of space beyond our horizon. The expansion that kept the universe from collapsing also stretched distant galaxies toward the event horizon and will eventually carry them past it. The dark energy that may have played a role in preventing gravitational collapse is the same dark energy that is now tightening the window. The quantum fluctuations that seeded all structure are the same quantum fluctuations that in eternal inflation produce a multiverse we can never verify. The conditions for existence and the conditions for ignorance are not in tension. They are the same conditions. They arise from the same physics at the same moment for the same reasons. The universe did not make itself livable and then separately make itself hidden. It did both things simultaneously with one process in one fraction of 1 second at the very beginning. Our existence and our ignorance have a common origin. There is a philosophical tradition that treats ignorance as a deficiency, a gap between the mind and reality that should be closed, a darkness to be pushed back by the advancing light of knowledge. And that tradition has produced the whole of science, the whole of our accumulated understanding of nature, from the orbits of planets to the structure of DNA to the temperature of the cosmic microwave background. It has been extraordinarily productive. It has given us everything we have discussed in this video and everything on which this video depends. But the ignorance we have been tracing here is not that kind. It is not a gap waiting to be closed. It is not a darkness that a more powerful telescope will illuminate. It is a structural feature of the universe, written into the equations of general relativity and quantum field theory, and the dynamics of inflation as permanently and as irrevocably as the speed of light. No instrument resolves it, no theory removes it, no future discovery closes the horizon. The boundary was built at the same moment the universe acquired the properties that made observers possible. It will remain as long as the universe does. And here is what I want you to sit with In whatever quiet remains after this journey, we know this. Not approximately, not loosely, not in the vague philosophical sense that there must be more than we can see. We know it precisely. We have measured the flatness of space to 0.5% across 93 billion light-years and followed the mathematics to its conclusion. We have calculated the minimum size of the actual universe from that measurement and found 32 sextillion invisible galaxies. We have traced the mechanism that built our horizon and found it to be the same mechanism that made our existence possible. We have located the boundary of what can be known from inside this universe, marked its position with the precision of a satellite measurement, and understood with clarity why it sits exactly where it sits. The boundary of knowability has been found, and finding it required the full apparatus of modern physics, centuries of science, generations of scientists, instruments of extraordinary sensitivity, and a mathematics capable of describing the structure of spacetime itself. The ignorance is not primitive. It is the most sophisticated ignorance in the history of human thought. It is the ignorance you arrive at after understanding as much as the universe permits you to understand from inside it. There is a kind of creature that the universe has produced on at least one small planet, orbiting an ordinary star in an unremarkable galaxy near the edge of a modest supercluster that can look out at a sphere 46.5 billion light-years in radius and calculate what lies beyond it. That can measure the temperature of light from the edge of the visible universe and read in that temperature the details of an event that lasted less than 10 to the negative 32 seconds at the very beginning of time. That can determine from the distribution of acoustic peaks in an ancient glow of microwave radiation the geometry of space across scales that dwarf any intuition. That can follow the mathematics of quantum fluctuations into an eternally inflating background and describe with precision the structure of a reality it will never observe. That creature is made of atoms forged in stellar interiors, assembled by chemistry that required billions of years of planetary evolution capable of abstract thought because of neural architecture shaped by hundreds of millions of years of biological selection. It is by any measure of physical scale negligibly small. The entire history of its civilization occupies an interval so brief in cosmic time that no analogy does it justice. Every war it has fought, every city it has built, every idea it has had, every measurement it has made, all of it fits inside a moment so short that the universe would not notice its absence. And yet it has done this. It has measured the shape of everything. It has traced the origin of structure to quantum fluctuations smaller than an atom stretched to the scale of the cosmos by an event lasting less than a nanosecond. It has found the boundary of what can be known and understood why the boundary sits where it sits. It has, with mathematics and observation, and the slow, careful accumulation of evidence across generations, described the architecture of a reality so much larger than itself that the description strains every concept it has available. That is not a small thing. There is a phrase that has appeared in various forms across the history of science, in the writing of physicists and astronomers and cosmologists, who have found themselves standing at exactly the edge we have been tracing throughout this journey. The phrase is something like, "The universe has no obligation to make sense to us." It is usually offered as a caution against anthropomorphism, against the assumption that the cosmos should conform to human intuition or human scale or human desires for tidiness and resolution. It is a good caution. The universe does not care whether its structure is comprehensible to the creatures it has incidentally produced on one of its planets. But the universe has apparently made itself comprehensible anyway. Not fully, not without remainder. The horizon remains. The 32 sextillion invisible galaxies remain invisible. The topology of space beyond our causal bubble remains undetermined. The full extent of the inflationary volume remains incalculable. The other pocket universes, if they exist, remain permanently unreachable. The deepest nature of dark energy remains unknown. All of that remains, and it will remain. But within the bubble, the physics is intact. The equations hold. The data speaks. The CMB carries the imprint of inflation in its spectral index, and its acoustic peaks, and its polarization pattern. The distribution of galaxies carries the baryon acoustic oscillation scale. The supernovae trace the expansion history. The gravitational waves, when detected, will carry the energy scale of inflation directly. The universe has left enough of itself inside the bubble for something inside the bubble to reconstruct with extraordinary precision what happened in the first fraction of the first second of existence and what the minimum structure of reality that emerged from that moment must be. That is a gift, an unrequested, unearned, structurally improbable gift from a universe that had no obligation to be legible and chose in its physics, if not in its intent to be legible anyway. The same equations that built the wall left enough fingerprints on the inside of it for us to read. Go outside tonight if the sky is clear where you are. Find a dark place away from the city lights and look up. What you see is a local sample, a neighborhood, a single page torn from a book whose total length exceeds any description available to human language. 2 trillion galaxies in the sphere above you, each one a gravitational city of hundreds of billions of stars, and beyond them, invisible, inaccessible, real 32, sextillion, more minimum formed by the same physics, governed by the same laws existing in complete indifference to the fact that you cannot see them. The light reaching your eyes tonight left its sources millions and billions of years ago. Some of it has been traveling since before the Earth existed, before the sun ignited, before the molecular cloud that would eventually become this solar system had begun to collapse under its own gravity. It has crossed distances that no human technology could cross in any time the universe has remaining. It arrives here, at your eye, at this moment, and ends its journey in the only instrument in the known universe capable of wondering where it came from. The observable universe is not a cage. It is a consequence. The boundary is not a wall built to frustrate us. It is a wall built by the same process that built us at the same moment for the same reasons, and we are the only part of it that knows the wall is there. That is not nothing. That is in the fullest sense available to physics and to language everything. The light is here now arriving, at the only eyes in the known universe, asking where it came from. It has crossed distances that erase all intuition. It has outlasted the stars that made it. And it ends, as all journeys through the observable universe must end here, in this moment, in this small warm brightness, burning at the edge of an incomprehensible dark. It is extraordinary, it is temporary, and it is ours.